utilizes FFA. And there was some internal debate inside ARM whether it should use FFA, which is a higher level protocol, or the SMCCC, which is a bit more basic. It's lighter, but it also doesn't offer as many features. And I actually wanted to show this diagram to make sure some things were clear. Plane 0 is on the left. I'm sorry, the colors don't work out very well here, do they? Plane 0 is on the left, and inside there we can run our VTPM service, and we can run a Lime service, which can sit on top of an FFA layer and SMCCC. Plane 1, which is a secure kernel, which would need to be able to do the Lime attestation processes. And on plane 2 is just the workload. And I've got two boxes in plane 2, one showing the ability to just use existing TPM drivers that use SMCCC, or alternatively the FTPM. Well, I think it's a long acronym, but there's a spec for an FTPM over FFA. So guest operating systems could use either of those using this model. And if we use the one on the left with the SMCCC, that driver already exists in the Linux kernel, doesn't need to be updated. FFA, the firmware FFA driver is being upstreamed, I'm promised, at this moment, but it's not in the kernel at the moment. So with our goal to provide lift and shift capabilities, we would like to be able to provide both of those. And this solution does that. However, I am asking projects like Coconut and other projects that are implementing interplane communication. This is somewhat of a change. So I think, Jörg, do you have a question?
Just a comment, basically. So the SVSM is not defined by the requirement for an SVSM protocol. There are other platforms that also don't have a strict need for an SVSM protocol. And I don't see a reason why the Coconut SVSM cannot support a communication mechanism like SMCCC. So I think it can be a platform for what you want to do in P0. Yeah, it's ARM's decision whether it wants to make use of it, but yeah, just that my comment from the Coconut side.
Okay. So is there any preference expressed for the use of SMCCC versus FFA? And if you don't know enough about it, I can go into some details on that. But the basic function of FFA is to provide a higher level of abstractions, which may not be necessary. As you can see, it's possible to do a TPM with CRB without using FFA. But the path forward inside ARM is to create new services using FFA instead of SMCCC. Because it provides more services. So is there any preference or opinions in anybody on that front? Yeah, please.
I think it's always very disruptive to disrupt the guest software ecosystem with new driver requirements. So like if they're functionally equivalent for you, why would you even bother doing the FFA version when you already have CRB done and working and upstreamed and in every distribution? Like it's just, I don't know. That would be where I'd put my
Okay, so the way we're proposing the Lime aspect, the attestation part, is it'll use FFA. Nothing existing uses that, so but it would still enable the drivers in the Linux kernel to work as is.
Can you explain why you need attestation of the TPM protocol when the TPM is already providing attestation of itself?
Yes.
It seems a little cyclical to me.
Well, no, actually, I would say it's not the attestation protocol. It's this is actually this is a bit of an eye chart, but the concept of this is exactly like the concept for AMD's SVSM. It allows the purpose of attestation for SVSM and for Lime is to be able to establish trust in the endorsement key, the generated endorsement key for an ephemeral VTPM, to an external relying party. So so the plane 0 or the SVSM implementation will request a platform attestation token and include in that token a hash of its endorsement key. That token will then get sent to the relying party, external relying party, which then verifies the attestation token and then can therefore establish trust that that endorsement key was generated inside a plane in this case.
But why does the VM need to participate in this?
Well, if you look in this back over here, the VM on the right doesn't have to participate in this.
But sorry, I mean, my question is, you said FFA provides attestation components. Why do I need attestation components in your command transport when the TPM already has its own attestation framework?
It's not providing it inside FFM. It's using FFM. So the Lime service in the center box.
FFM now.
Sorry?
What's an FFM?
Sorry. I don't know. What was it? FFA. Sorry, FFA. It's not inside FFA. It's using FFA.
But that's I don't understand why that's there. Like why?
Why use FFA?
No. Why do I need attestation? Why do I need yet another attestation?
Let's see. It's basically it allows a relying party to establish trust in the endorsement key for the TPM.
But the TPM should do that itself, shouldn't it?
Not in that case. TPMs typically have a persistent endorsement key, and you have that through a back-end supply chain solution where you establish that trust.
But if you're using an ephemeral key, I would sort of have expected that the TPM itself would go down to the RMM level and get some sort of attestation that it bundles up in its own attestation reply.
Yes, it does. Oh, yeah, you do.
You'd have a notes and all of this and stuff, but like that's what I would have naively expected. Like it would have all been bundled in the TPM protocol, not layered on top.
Yeah, go ahead.
Maybe the point is, how do you know that EK is related to the TPM you're talking about? You're the VM. That one VM, you could just plug the TPM to another guest, and you know if they're talking your guest or something else. And this way you could make sure that the SVSM that you're talking to is really the one that you're expecting. It's just an attesting the service, not the TPM itself.
I'll give him the mic. Sorry. It does, yes. And we modeled ours on that one. Sorry? Yeah, of course. It's all early days. We get it.
Okay, I get it. But so, like when everybody's defined the attestation, authenticate, what's the right word here? When we talk about like PCI device assignment, there is a step where you say this memory address is actually, belongs to the device that I think it belongs. And it's very similar to what you're talking about here. It's not quite attestation, but it's like you're just asking the RMM, does the data that I think I have be the data that you think you have?
Okay.
So close, sorry. So the question, I have a different question. So why do you actually need the protocol? Because typically, I mean, these things are already VM is running the OS and it knows how to do these protocols. These protocols are not new. So, but you're saying that you need protocol from guest OS, I don't remember how it's called, plane, whatever, non-zero.
Plane 2
Plane
on
2,
the diagram?
let's say, plane 2 to plane 0. So you need a special protocol because we were able to get along so far, at least, without any protocol. So the question is, Intel, which was presented just before. So we actually using VTPM and SVSM, and we just use, private MMIO as a communication. So why do you need the protocol, the new protocol?
I would say so that when you've got a plane 2 workload, it doesn't actually care what is running in plane 0, whether it's Coconut SVSM or, as an example, our prototyping work has been done on Linux KVM in plane 0, or some of our other prototyping work has been done with just a very bare metal partition manager. If you have a well-defined protocol between that, then you don't care who you're talking to. And
so just Hypervisor agnostic is the only reason you're saying?
I would say Paravisor agnostic.
Paravisor, because we are talking about
Yeah, exactly.
Okay.
So,
but no any other technical limitations which you encounter apart from this agnostic convenience?
No, right, none that we've come across. So yeah.
Thank you.
Sure, thank you.
So regarding this earlier question about why do we have this, so we need this SVSM attestation thing. Why does it not go through the VTPM itself? And why is there this separate protocol for it through the SVSM? One thing to think about is that not everybody who is using the SVSM necessarily has a VTPM. So there are other cases for this, and there might be some users who don't have that at all, but still need to attest the SVSM. So that's one reason why you might have those be separate.
Thanks. I have a completely different question. Since you have FFA already implemented in the normal world VMs and possibly in the secure world partitions, would the VMs inside of these planes be able to use FFA to communicate with the hosts and with secure services?
Yes, they could, depending on the policies enforced inside the RMM. By default, the RMM sends all SMCs from any PN to plane 0. It can, we don't have any configuration options on it, but then everybody gets to write their own VMM anyway. They could reconfigure the VMM to send those to the secure services instead of sending them to plane 0 in that case. If that's it, then thank you. That's not as controversial as I thought it might be, so thank you.
Thank you, Derek. The next one, Jason, Derek. We'll keep going. We can have the discussions going later. But the next one is by Chris on OpenHCL.
Hello, I'm Chris. I work on the virtualization team at Microsoft. I'm here to talk about some of the work we're doing in the confidential space with OpenHCL and our Paravisor. Oh, sorry. So real quick, I want to define what we define as a Paravisor. So it is a firmware component that runs inside the guest at a higher privilege level. And specifically, it provides emulation for the unenlightened guest. So that's APIC emulation and interrupt virtualization, and it can provide multiple services like a VTPM or device translation or legacy emulated devices. You know, it's essentially a full VMM running inside the guest. And of course, you know, you're going to ask, well, why do I want a Paravisor instead of an SVSM? The answer is you want to run guests that are not fully enlightened. So that's guests like Windows, guests like older Linux distributions. And you want to provide standard device interfaces. So that's like, well, instead of having to do, you know, different attestation protocols or SVSM protocols, you can use TPM via existing MMIO drivers. I'm going to give a very brief overview of OpenHCL. I have a BOF session later today. That's where I want most of the, I'm happy to answer any technical questions, but I don't want to kind of derail this conversation here since I want to kind of talk about, you know, Paravisor and how it intersects with the rest of the CC community. But essentially, it's a very minimal Linux kernel with a user mode VMM written in Rust. We are open sourcing this later this year. This is kind of the architecture of what's running inside the higher privilege level. You know, we have some processes. We have this MSHV VTL driver that manages all the virtualization APIs. Kind of if we think about our design philosophy, you know, we want to minimize our kernel changes. We want to do as much in user mode as possible. This means, you know, doing device drivers, doing as much logic in the user mode VMM as possible. You know, we write Rust. We want to write as much safe idiomatic Rust. We don't want to use unsafe except when absolutely necessary. And we want to keep the VMM code OS agnostic so we can run it, you know, in other environments even outside of the Paravisor. You know, can talk a little bit about the VMM worker from the previous slide. It's basically just a VMM process. We handle exits. We have per VP executor threads for performance. Again, I'm not really going to go too much in detail here because this time section is very limited. The questions I really want to pose are, you know, this is kind of a starting point. You know, at Microsoft, we find a lot of value in having a Paravisor. You know, could we have a single code base that supports both an SVSM and a Paravisor, right, with Coconut? Could we run the Open VMM user mode in Coconut? You know, how our TDIS device is going to work? So kind of just opening the floor for questions and discussion.
So I actually see a lot of value of running your Rust user space on Coconut SVSM. And I'm really keen to learn from the code you're open sourcing what is actually needed in Coconut SVSM to make that work.
Right.
Because right now it's, of course, not there yet. So Coconut is not there yet to run it.
Right.
But I'm very keen to learn what's needed to run it there as well.
Yeah, and to touch on it really briefly, like there are multiple avenues you could go to implement a Paravisor in Rust, right? You can imagine we could have gone down the Coconut SVSM path where we write no standard Rust, but we found writing no standard Rust is very hard, right? It's very hard to accomplish certain things. It's very hard to be effective, right? So we look to utilize the Linux kernel to provide a standard Rust interface so that we can write standard Rust code, use standard crates if we want to, have a lot more flexibility and use other tools of Rust to get us the performance that we need.
Right, yeah, so one thing we definitely need for that is to have a standard Rust target for the Coconut user space. So that's probably one of the most important things to have.
Exactly.
Right, so.
So one question, I think this OpenHCL thing provides a VTPM thing.
Yes.
We also have just heard about Coconut providing a VTPM thing.
Yes.
Is there some collision there? And also, I think, do you think there's any answers from your implementation of the VTPM that might be useful in some of the questions that we've just been scratching our heads about for the Coconut, like persistence? I think yours is stateful, but I don't know if it's trusted or anyway.
We support both ephemeral and stateful, but we've seen the discussions about stateful TPM can be contentious, maybe, or interesting. I think really the Paravisor cannot make certain guarantees about even when your TPM is stateful. Unfortunately, my background is not really deep in the attestation space, so I can't unfortunately answer a lot of questions here, but we can discuss a little bit more here or in the BOF. Like, do you want me to talk a little bit more, or are there any other things that people wanted to ask?
So what type of events do you need to handle, and do we even have all of these events available as part of our VTL1 code? So in your case, VMPL0?
Yeah, so we actually support running both in SMP TDX with partitioning or in Hyper-V VSM.
But it means for something like Coconut to integrate there, you would need to have some interface that basically tells you,
we
hey,
would need
please
to
tell
have
me on this MIO trap, on this.
Exactly. We would need to have Coconut expose basically kind of like a virtualization interface similar to MSHV or KVM or WHP that allows the user mode VMM to get all the exits it needs to handle emulating whatever the unenlightened guest needs.
Okay. At which part you really are completely also, even though you're running in that user space or potentially special user space in Coconut, you would still be part of the full TCB because you effectively have full
This
access.
is a Paravisor is part of your full TCB, yes. Because you are trusting, especially your guest is unenlightened, right? The unenlightened guest and the customer, you are trusting the Paravisor to provide security and enlightenment.
Well, you don't have to go there. You could do an in between where you basically have a fake shared state between your more or less unenlightened guest and your Paravisor, where the Paravisor only has windows of access.
Yeah, you could design it like that, right? Today, these all run within the same address space with VTLs or VMPLs.
So if your guest is unenlightened, how does it get to know and learn that it actually runs in a confidential environment at all?
It doesn't.
So what's the point then?
That's kind of the point, right? Like, you want to run a workload that wouldn't run in a confidential guest.
The answer to that might be to reduce liability for a cloud service provider, just being able to take an existing workload, run it in a confidential VM, and even if the customer didn't ask for it, then they can say, well, we just never saw your data.
There are a lot easier ways to achieve the same thing.
So you need guest enlightenments to run confidential compute workloads today, and this is lift and shift.
I understand. It's just that if you completely lift and shift without any enlightenment, then you don't know as the guest that you're now actually confidential. I could be lying to you, right? I could put you in an SEV SMP thing with a backdoor, and then or in whatever confidential environment with a backdoor, and you wouldn't even get to know about it because you don't have the attestation flow going because you're unenlightened. So,
right, but the attestation is running in the Paravisor. So the Paravisor is performing attestation to provide security guarantees.
I mean, it just sounds like you're providing confidentiality as a
Right,
service, right? There'll be a tick box on your web that says,
This is
yeah,
one
I
way
attested
that you can provide confidentiality, right? If you think of confidentiality as a spectrum.
But if you have unenlightened
of
guests, don't
things
you
you can
also
do, right?
have all shared pages and all shared memory in the guests? Like,
So kind of getting really into details, but here pages are private by default. The Paravisor will only make pages shared as required to perform I/O or do operations like that.
which is somehow magically done with paravirtualization.
Yes.
Okay.
And they do have a VTPM so there is some guest could know. They do have a TPM here, right? So you can have an unenlightened guest that might not know anything about confidential attestation, but it can at least do some kind of attestation and see, oh, it's a TPM. And then, yeah, the guest itself might exactly know, but it might not know everything. But a client can know, oh, okay, cool, I'm using, Azure or whatever. And I don't work there, by the way, but I'm using Azure or whatever, and I expect them to have this TPM present, and I am going to think that that proves something or other about the kind of guest that I'm running. And there's some kind of guarantee there. Up to you if it's completely rigorous, but an unenlightened guest can have a sense of confidentiality.
So just wanted to mention that the use case for Paravisor is not only fully unenlightened guests, but also less enlightened guests. So what a Paravisor saves you, for example, is to implement something like a VC or VE handler in the guest, or to make the guest have code in the guest that modifies the page tables to set a C bit for everything encrypted, right? So
or handling interrupt virtualization, right? Like
right, or handling interrupt virtualization, which is very important on the AMD platform, for example. So
you can imagine like how invasive supporting secure interrupts is to an existing operating system.
Right. So I think even Windows has some enlightenments, right? It
Yes.
has even it understands the concepts of private and shared memory, and it understands the concept that it has to use shared memory for DMA because it still uses the devices used by the Azure hypervisor for performance reasons. So there's still room for Paravisor even with some enlightenment in the guest. So
I believe there's a question over there.
So you mentioned the attestation is part of the functionality that firmware provides. Could you tell us more? What else does it provide?
Sorry, can you restate that last part?
So could you tell us more? For example, what else does it do for the unenlightened guest? Like, does it improve security in some way, for example?
Right. So you can think of the Paravisor is a much smaller code base than the whole guest operating system. So especially as we really see the value in Rust and doing all this, being able to provide security to the guests by like filtering interrupts and filtering device accesses through the user mode VMM in Rust, we believe we can provide more security to the guest than trying to harden the whole guest itself.
So which kind of security improvements you can do there, and which kind you have to do in the guest?
I mean, you can do anything in a guest, right? The question is,
yeah, but what do you have to do in the guest?
You don't have to do anything because the Paravisor could. Our Paravisor today does require, some enlightenment in the guest around page visibility, right? But the guest is still using, existing Hyper-V paravirtualized storage. It's still using existing interrupt management, right? It doesn't have to manage like attestation or those kinds of things.
So to answer your question, like about what do you do like in OS versus what do you do on Paravisor or whatever you call it, with privileged component running inside a guest. So we have, let's take Linux as an example of OS will be running. So we have done a lot of work exploring what would it take to harden Linux. and what kind of invasive changes it would take, you know, to be merged and so on. So, and we also compared it to what it would take, like, you know, to do these changes in a Paravisor. So, and the conclusion and, you know, the feedback from Linux community definitely was that, you know, some of these changes are so invasive that, you know, maintainers don't want these changes, at least now, while maybe there's not enough exploits visible. So that's why there is, like, definitely value in having a Paravisor where you can proactively put these defenses. So if you're interested, we have talks online also about this topic. So
there was one yesterday about spectral mitigation by just simply, unsharing pages with the guest, right?
Yeah, so it's not just speculation attacks, it's everything. So you can do, actually, there's a lot of additional things you can put into Paravisor. So it's like you can look at the whole threat model and seeing, okay, which things you care about, what attacks you care about, what do you think is unrealistic to do on the OS side, and, you know, what you can actually do on the OS side, because it also depends if you're running workloads, just if you're okay running it behind a Paravisor, or you want to run the plain OS inside your confidential guests. So it's all the trade-offs, you know, you as a CSP or TENS will have to do so.
So we were here for, I guess, 1 hour, 1 hour and a half, and we saw 3 Paravisors being demonstrated. I guess there's a common theme that all of them are featuring a VTPM. Can you share with us if some of the other, questions that we try to answer here, how they were answered in OpenHCL, for example? Do you have a network stack? Are you extending the EK, or are you deriving the EK from the underlying hardware root of trust? How are you doing that?
Yeah, unfortunately, we're like at time, right? But
I can catch up with you later.
Yeah, this is best left to probably another forum. But, you know, there are things that the Paravisor can do, and there are things the Paravisor cannot do. So I think James wants to interject.
I'm going to answer the question. I'm just going to point out you have a BOF coming up
Yes.
where we can actually go into more detail on this rather than derailing this session.
Yes. Yeah, I mean, we're out of time, so.
Yep.
Thank you, Chris.
But actually, we do it. So Microsoft does it the old way that we used to do it with SVC. Wraps the attestation.
I have Osama here for his talk on attested TLS.
I don't remember. Do you guys have a network stack?
Guys.
Special device?
Folks, we have another
So
speaker.
Yeah, you could strip that out too, right? I don't know how much you get at the kernel.
Yeah.
So let's.
All right, so I'm Osama from TU Dresden, and this is joint work with Thomas Fossati, Hannes Schofenisch, and Simon Frost. And what we basically wanted to analyze here was what are different ways of different ways of doing attestation at different layers of the stack. What are the kind of security comparisons between those? And I believe that all of the solutions that existed out in the space of confidential computing are completely broken. And that's what I am going to show also in this talk, and to find better solutions and what are the limitation technical challenges around there. So that's a kind of a comparison between all the space that exists. So specifically, I want to give a little bit of a background so that everyone is on speed for what is TLS, what is attestation, because in my feeling, so some people are experts in attestation, but not the others, and the other way around. So let's quickly recap what TLS is. Specifically, I will talk about the TLS handshake protocol, which means that basically and I take a specific variant of TLS, which is with client authentication. This is optional, and the server requests that it wants a certificate from the client, which is via this certificate request message. And if it requests, then the certificate and the certificate request messages, which you see certificate and certificate verify messages will be sent over by the client over to the server in order to be verified, which then creates a secure channel between that. Secure channel in this sense has
Can I just ask, that
Sure.
is DH verification, not DHE verification. It's not ephemeral. It doesn't have perfect forward secrecy. So the new standard for TLS is we set up the secure channel first, then we authenticate the ephemeral, the DHE version.
So this is doing actually DHE client hello, server hello is actually exchanging these messages, and this is secure channel. So you have forward secrecy, right?
Okay,
so client hello
the secure channel is actually set up here, and then you do this verification. That's all I was. The secure channel is actually set up at this point, and then you do the certificate verification to make it DHE.
So that's not correct, because at that point in time, so going by the NIST definition of secure channel, it is when the client is also authenticated, and the point that you were pointing to, that is just for online audience, which was here, it's actually not a secure channel, it's a one-way authenticated channel. So if you don't have these two messages verified, you don't have a secure channel, you have a one-way authenticated channel according to the NIST definition.
Okay, thanks.
Please speak on the mic, please. Okay, so she's just agreeing with me, just for online audience. So this is all coming from our research of 2 years. So of course, like, but please feel free to just be on the same page. So if you have different understandings, feel free to interrupt me anytime. So this is supposed to be a discussion forum rather than just presenting. We had one floor down yesterday, the CC Summit, which was all pre-planned. So I don't want to have that kind of thing. So I'm here just for discussion, which I like, of course. So the secure channel, going by the NIST definition, requires the client to provide its certificate, which is requested in this specific optional message, which is the certificate request message. So, okay. And the problem here is that TLS provides, so this is not the problem, of course, it's good for network security, but the problem is that it's not good for endpoint security. I know that I am communicating with somebody out there in the wild, but I do not know what is the status of the key which it is using. I'm blindly trusting that that key is really in possession of that specific entity which is claiming to be person XYZ or some service XYZ. So the idea is that I need more for confidential computing, which is it really the workload that I'm trying to communicate with or not? I need even more than that. I need lower guarantees. Is it really the platform that I trust? And platform I define as the hardware, bootloader, firmware, all included. Of course, there are disagreements in all that, what we define as the platform itself. But the idea is that we need a different guarantees for all of the stack, not just that I am communicating with a piece of, let's say, software which has possession of that key. So TLS provides proof of possession via that certificate message, but it does not provide that what software was running on that stack. Was that piece of software actually protected by some confidential computing guarantees? And this problem is not the real problem. So the problem is solved many, many years ago. So we have remote attestation. Many of you who are old enough know TPM, and there were already presentations of TPM. Yes, please.
Question.
Yeah.
So
yes, please.
You said you don't know that you're talking to that exact endpoint, but if you've got a key distribution service which will only hand out a key to an endpoint once it's verified all of this, then surely by talking to something with that key, you do know those properties.
No, I would disagree, because if for instance, I have that certificate, right, and I leak out my key to you, for instance, it's not you, it's not me who is talking to that person X.
Okay.
Right, so I could leak out until I have the guarantee that that key which I am possessing, the certificate which is issued by the certificate authority, if it was really protected by me or not, whether that key was running on some confidential computing workload or whether it was running on some genuine, let's say, just a normal server. So it could be leaked out.
So the problem really is that you have potentially conflicting information. The TLS has very specific information, or the TLS key has very specific information and very clearly defined information about the entity. That is not necessarily the information the entity itself has or needs to provide. For example, a VM can be identified with a system UUID. And actually, that's what I would be using when trying to check, is that really the VM I'm thinking to talk to? But that's a UUID. That will never, ever show up in the TLS key or in the TLS certificate. So the TLS certificate says, right, I'm this name. But is this name correlated to that UUID? Might or might not. Who's going to tell me?
Yeah. Somebody had a question here, or is it? Okay. So as I said, so remote attestation already exists. So the problem statement that I posed here was just a starting discussion, which is that we know remote attestation, VTPM, where there were already like 2 presentations, and also for the workloads, we have now the same concept applied to the confidential computing domain. The key idea of remote attestation is three things from a protocol perspective specifically. I generate an evidence. Secondly, I transmit over to the second party. And thirdly, I need to appraise it, which is a fancy word just coming from RATs for verification. So I verify that evidence. So evidence, just a name for, let's say, SGX code or AMD report or ARM CCA token, I think is what they call it. So the idea here is that I'm using the RATs terminology here. So if you are not familiar, so the idea is that this is the attester, which is actually the entity under test, confidential computing workload, or the confidential VM, or confidential, let's say the enclave, or whatever it is. So this is the attester. And the other party is it defines three roles, but I combine the two just to be very simple. And this is the verifying relying party, combining the verifier as well as the relying party who is actually interested in knowing what is the status. So this is, if you are the workload owner, for instance, you are here the verifying relying party, assuming you have the verifier inside your own. So the way it happens is the protocol, from a protocol perspective, it should send out a nonce, and there are now, so again, some terminology, a testing environment and target environment. So this target environment is the one which is actually being checked. So this is the confidential computing workload or the enclave, for instance. And the testing environment is the one which will actually collect some claims. We need some root of trust which will actually collect the claims and then send it over to the relying party that, hey, this is the thing that, this is the current status of that enclave. So there is a generation of this evidence, which is actually including three main things. The first one is it samples the claims at some point in time, stores it in some shared registers, for instance, and then the the attesting environment will then collect out these claims at some point in time, which could be later on when the request for attestation comes. So it could be not necessarily at the same point in time. So if it's runtime measurement, it could be same, but it could be the boot time measurements as well. And then typically you also need to protect these measurements because they will travel over the network back to this point, back to the verifying relying party. So typical way of doing it is by signing. It could also be MAC, for instance. And for instance, if it is local attestation, it could be MAC, which is faster. So the real problem statement is, how do we combine the two things, remote attestation and TLS together, so that we can have not only the guarantees about the network security, which are done by formal verification of the TLS protocol many, many years ago, like 2018 when it was standardized, TLS 1.3, but also about the workload and the platform on which this is running. So that's the real challenge. And the idea here is that we have explored all the design options which are there for attested TLS, and we kind of categorize them into three main categories, which is pre-handshake. So we have two things now to combine, which is attestation and TLS. I can do either the attestation first, and the most important part here is the signing of the claims. And that's where it's defining if I do before starting the TLS handshake, so time going to the right. If I do before the TLS handshake protocol has actually started, this will be pre-handshake attestation. If it is within that, so it's kind of amalgamated between that TLS handshake, so it's intra. And finally, if it is after the end of the TLS protocol, for instance, using the exporters, it is post. So with these three design options, just to quickly give you an idea of how do they compare with each other, the idea is that pre-handshake attestation, as I said before, the protocol has actually, TLS handshake protocol has actually started, the generation of the evidence already happens. So it can be way before that. And that's the problem actually in the pre, where it can lead to the relay as well as replay attacks, which is kind of the problem. That I generate at some point in time, I can replay it across any sessions. There is no link between the generation of the evidence and the TLS handshake protocol, which will run afterwards and can be way later afterwards. And just a crazy thing that Microsoft and Intel are doing, they generate certificates valid up to 2050. So large window to do a replay attack. Anyway, so this transmission of certificate happens within the TLS protocol. And then finally, there is the appraisal of the evidence, which happens at the end of the other party. Second variant, intra, what happens here is that we have the nonce coming within this encrypted extensions. And with that nonce, it is generated, the evidence is generated within the TLS and is valid for that specific handshake. It cannot be replayed across any other sessions because it has that specific nonce and these parameters that it negotiated in the first phase. and appraisal happens within the protocol again. Third variant, post-handshake, how it happens is that it establishes a secure channel, just like before, without any attestation at all, and then it uses the exporters to generate that evidence after the secure channel has been established, and then there is a delay or a latency of half round-trip time that it has to now transmit the evidence over that secure channel. And finally, the appraisal happens, which is afterwards of the TLS handshake. So in this picture, I'm showing everything that I have presented until now. So with the design options within these three, so pre, intra, post, and within that, it can either be self-signed. So within the pre-handshake option, we have either the self-signed, so it self-sign that certificate, which is what Intel's RATLS does. And the two options that I just mentioned about, which is this Open Enclave by Microsoft and Intel SGX SDK, they generate certificates valid up to 2050. Big problem. So TA issued certificate, which is the second option. Here we go to the trusted authority, say, hey, check our evidence, provide us a token, and that we can use over for the next session. And that is basically what Verizon is doing, or Verizon. So the CA issued certificate is the third option. Within, let's say before using that session, so the server and the client I showed, I go to the certificate authority, I say that instead of issuing a normal certificate, within that certificate signing request that I send to the CA, I say that, hey, this includes also my evidence. And that CA now has to be modified to check also my evidence that verifies and then issues me a token which I use and afterwards. Again, a replay is possible here. So if someone gets hold of that token which was sent back by the attested signing request as part of the certificate, that can pretend to be me. So that's, again, a problem. So intra, we have two options. We can either do some negotiation, what kind of format. So we have a number of options. Intel SGX has its own format, SGX code, TDX code. AMD has its own format. ARM CCA has its own format. So how do we negotiate about which format we are going to do for generic things? So that's something which can be done via negotiation within the TLS phase. Server hello and client hello. Within that, the negotiation happens that, okay, so I want CMW. Can you support CMW? That says, yes, I can support CMW. Yes, okay, so we go with CMW or SGX or whatever. So that happens as part of the negotiation itself. Final option that is the post-handshake. It's used in SCOAN. But the bad thing that they do is actually they use the exporters, but there are three. So section 7.5 of TLS 1.3 talks about RFC 8446. Talks about this exporter thing. That's already provided by TLS, so that's the functionality that they are using. But the problem is there are three inputs to that: context, label, and key length, and they use all of them as constants. That is, they have a specific constant that they use for label. They have empty context, and then they have a specific key length. So every time I will call these exporters, that will give me exactly same thing. And this is what they are using as exporters. So which is, again, a problem that I can replay this for any number of times. So I will, so this is what I wanted to discuss. If you have any other design options, if you see something missing here from any solutions, up till this point, I claim to be fully exhaustive of what we know of. So below this line that all of these are examples. Of course, we know that there is AMD is not in here, RISC-V is there, but many other solutions exist, but we hope that the first layer category, which is all design options, are hopefully covered. Unless I missed something, I would love to hear about it, please.
Not missing. I mean, we had similar questions when designing the NVMe TLS thing, which we did. And what we chose upon to not try to meddle with the TLS protocol itself, meaning not meddle with the handshake, insert magic values here, because that would require you to modify the libraries themselves doing TLS. Sure, yeah. Which means that would be in that security critical path, yeah. Which means your code really would need to be audited, everything, blah, 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 blah. Where we said, we found it a tad too risky. We'd prefer to keep the libraries intact as they were, because then we are sure we haven't tampered with the integrity and security analysis of existing libraries, so we could just use them as is. That's why we essentially did not try to look into modifying that thing. Sure. Similar for the post attestation,
The problem with the POS attestation is at that point, the TLS connection is already live. It's live, but you don't know whether you should be talking to it or whether you should be sending IO over it. That turns out to be really, really tricky. How do you avoid having someone sending IO or sending any data over a channel which is already established? So you end up in some sort of established but not established phase. And so you have a connection, but which is not actually a connection, and something. That was also really, really hard to model in code, because while it's quite easy, right? You have a socket, open a socket, talk to it. Now you have a socket, open a socket, and talk, but not really talk. And would you mind holding off? No, it doesn't. You can't really model it securely in the existing flow. So that's why we came to the first solution, right? Do the attestation before establishing the TLS channel.
Okay, so I will firstly quickly just answer the first one first. So there is standardization going on in the TLS working group, which is a draft which is with my co-authors, Hannes, Finish, and so on, are co-authors in that draft. And TLS working group has a very high security standard for setting out the standards. And that's basically, they require formal verification. So we will do actually the formal verification work. We will standardize in the IETF. We have the proof of concept already implemented within that intra, and that's what we will have this line of chain of the work. So that's not really, we will throw out something in the wild that, okay, use the TLS with broken guarantees. We will actually formally verify. That was one of the things I didn't talk about, but anyway, so we will have the formal guarantees. To quickly wrap up okay, yes, please.
Yeah, so the break started. I think everyone is probably in need for a coffee. So this were interesting discussions, and we can probably continue that during the break. So thanks for the presentation.
Thank you very much. Thank you.
And see you all again at 12.
Hey, folks. Alex. Alex. Is this mic working? So do we lose our notes as well? This microphone?
Because our notes also gone, right?
Yes. They said they rebooted something. Is the mic on? Hey, folks. Guys. Alex, Samuel. Take a seat. Okay. So we have a couple of technical issues that we are trying to resolve. We should be going in another couple of minutes.
Yeah, the room is like 24 minutes old.
Yeah, they said they rebooted it. Huh?
Yes.
Hello everyone. I am Muminul and my colleague Zinan. We work for Linux Systems Group at Microsoft. So today we'll be presenting the performance between KVM, QEMU, and Linux root partition on Microsoft Hyper-V with Cloud Hypervisor as the VMM. So we think community would be interested to know about the virtualization stack that we have been building for a few years at Microsoft. So let's get into that stack a little bit. Traditionally, at Microsoft, we have the Microsoft Hypervisor, and Microsoft Hypervisor is a type 1 hypervisor. You know, like the type 1 hypervisor has a root partition that communicates with the hardware to, root partition communicates with the Microsoft Hypervisor to create and manage VMs, to orchestrate the VM lifecycle management. LSG have been working, and for the root partition, we have been using Windows for a long time, and LSG virtualization team has been working to an alternative operating system, and we brought up Linux as an alternate solution of Windows. So you can say like Windows root partition that can actually create both different types of child partition like Linux, Windows, and PSD. We are trying to do the same on the right side, where we are using Linux as the root partition on top of Microsoft Hypervisor. So in our MSSB-based virtualization stack, we have the hardware, then Microsoft Hypervisor in the Linux root partition. So we have a Linux kernel module, the dev MSSB, that's similar to, like, some sort of similar to dev KVM that manages the virtual machines. And for the VMM, we are using Cloud Hypervisor. That is a lightweight and Rust-based VMM, which is also a member of Linux Foundations. So let's talk into the confidential VMs on KVM QEMU. So we have the AMD hardware, and on top of QEMU KVM, we have the firmware OVMF or UEFI. So since attestation report is an important part of the confidential VMs, let's see how we can generate the attestation reports. So one of the tools that is used to generate the attestation report is Save SMP measure. So here the tool needs to have the OVMF FD, either the source or the blob, and it provides the hash to actually verify the measurement later. So for the next few slides, when we talk CVM, we mean AMD 7SMP based CVM, since we know the CVM is supported on both Intel TDX and ARM CCA. So on the confidential VMs on MSSB, we have the similar hardware, AMD hardware, and Microsoft Hypervisor and Cloud Hypervisor, but instead of using some like OVMF or UEFI firmware, we are using IGVM, the IGVM file format that made by Microsoft. It's called Independent Guest Virtual Machine. That's a file format there, and that is actually IGVM file is generated by a Python script that Microsoft already open sourced it, and that has the script has Linux loaders in it, and it embeds Linux kernel and initrd, and create the VMSA page on the fly, and create an IGVM file that will be later used to load the guest. And that supports direct kernel boot. And also, once the script generates the IGVM file, we get the hash. The one issue with this script we have at the moment, we have to provide the SFA table dump, and that we need to depend on some other open source tool, like some SFA utility tools. So for the next few slides, my colleague Jinan will be presenting some numbers, comparison between KVM and Microsoft Hypervisor stack.
Sure. So first, let's try to understand the test setup, right? Like, what are we testing, right? So we had two different setups. In the first setup, we are running, in both the setups, like we are running like MSHV as the L0 hypervisor and Windows as the root partition. But in the one setup, we are doing MSHV as the L1 hypervisor, and on top of it, we run Cloud Hypervisor as the VMM. In the other setup, we run KVM QEMU as the L1 hypervisor, and on top of it, we launch like nested CVM guest. So what we want to test is like the performance difference between nested CVM on the MSHV stack versus the KVM stack. So we did like a couple of experiments. The first one is like the network throughput test. If you want to see the hardware setup, we have like a AMD EPYC server with like 1 TB of RAM, on which we launch an L1 VM, which has around 16 CPU and 32 gigs of RAM. I performed the test in two different modes, in a single queue setup and a multi-queue setup. So I'm using like VirtIO NICs to do all these experiments. And I basically run like in a 10-tap interface with single queue and multi-queue with different VM sizes. Like in a single queue setup, I use 1 CPU and 4 gigs of RAM. And in multi-queue, I use like 8 CPUs and 8 gigs of RAM. And if you look at like, I'm comparing 4 different things right now. The first one is the base thing, right? Like where I just launch a nested guest, and I don't do any SNP stuff, right? Like I just do a basic nested L2 guest on the same machine which has like the SNP thing. And then I do a KVM, QEMU, nested KVM. Again, then I have like two MSHP specific setups. In the first setup, like where we do like remap the GSCB page into the VMM, and in the other setup, we don't do the remapping into the GSCB page and instead use the hypervisor hypercalls to update the GSCB mappings. This turns out to be like a performance issue, right? Like because if you have to update GSCB page, so GSCB page is usually updated when you are handling like VMG exits, and these happens often when you are doing like network IO throughput as part of your MMIO exits, right? So it turns out that the mapping GSCB page into the user space is like a lot helpful, as you can see from the graph as well. That we were able to reach as close to KVM when we started mapping the GSCB page into the user space process. There are still some outliers in case of multi-queue setup. That is again like a design choice in the hypervisor, in the Microsoft hypervisor, that whenever the VMM gets access to, for example, like the shared pages, it needs to do an additional hypercall to actually gain access to those pages. Because of that, like we are not as performant as KVM in case of like multi-queue setup.
One question.
Yeah.
So you are not testing the non-nested case at all here. There's no comparison
Non-nested
there.
is not tested.
Do you have some intuition about what that might be like?
It's more performant than nested.
Okay.
Just one question. So the fourth one is no SNP for Microsoft one, but no equivalent for KVM.
No equivalent for KVM. I think the numbers are very similar, so I did that testing as well, but it was getting too clumsy to put out there.
Okay, yeah, that's why I was wondering how to read this slide.
Yeah.
Okay, thank you.
We did a similar kind of testing with the block IO throughput as well, in which I do like two kinds of operations, like random read writes versus non-random read writes. And the observation was very similar that we observed in the network throughput, right? Like KVM, like with remapping, we were able to achieve as good performance as KVM QEMU, and without remapping, we are slow. We did some CPU stress testing as well, just to make sure, right? Like so the CPUs are also as performant. There were like numbers were similar, so there was nothing interesting that we observed here. But we have like few discussion points, right? Like my colleague mentioned the ACPI tables, right? Like we need to dump the ACPI tables while generating the IGVM file. But ACPI tables usually contains like a lot of dynamic information. And for some of those dynamic information, currently we have some PV interfaces, for example, like CPU count. We expose it via PV interface, but ideally it should be exposed in ACPI table in one of the tables, right? Like the MP table or something. But yeah, we want to get away from these PV interfaces and like natively use ACPI tables. But the problem there is like, as soon as you start putting this information at the time of IGVM generation, you will end up with multiple IGVM files and you will end up with multiple hashes that you don't want to manage. We're also looking into like alternative CVM native firmware like TDSHIM and not use UEFI because the binary blob size of UEFI is huge, and that affects the measurement time, like that affects the boot time as well, because we want this to boot very fast. Like in our testing, we observed that like hashing a page takes almost like 2 milliseconds per page, and if you have like a lot of things to measure during your boot time, then the boot time is always slower if you were to use UEFI. But I know that TDSHIM does not support AMD 7SMP at this point, but there's an open code request, or there's an open discussion going on that TDSHIM should be supporting 7SMP as well. The other thing is like, there's another design choice in the hypervisor where it requires that all the guest memory to be moved into exclusive state or encrypted state before the guest is started. And initially we were using like 4K pages, and that was taking a lot of time to do that hypercall. We moved on to using large pages, but even then, if you have like huge amount of memory, like 200 gigs, that takes a lot of time to boot. I don't know how is the situation on KVM, so I would like to hear opinions from folks around here. We also want to support live migration at some point in Cloud Hypervisor, so if folks have ideas, thoughts,
Okay, it was. With regards to boot time optimization, as I understand correctly, the problem is that you are hashing the memory pages using just one CPU. right? Couldn't you split the memory into blocks and hash using multiple CPUs every block, and then hash the hashes of them?
The thing that hashes is the AMD security processor, which is a tiny ARM core. Alongside
the PSP processor which is hashing.
Okay, thanks.
Yeah, I mean, the only real optimization for boot time hashing of guest pages is lazy acceptance.
So we do that as well. So we only measure like our kernel and the initRD, but the thing is like sometimes initRDs also explode a lot, and yeah.
Why are you measuring the initRD as part of your launch digest? You don't need to. As long as you take a hash of your initRD and the hash of your kernel, and you have your initial firmware validate those hashes, you reduced your measurement time, but still have the same guarantees.
Yeah, so currently we are doing direct kernel boot, and we cannot move to that approach, right? As soon as we go to like TD-shim or something, I think we can use it with DM Verity, right? Like we can use like initRD in a root file system, and then use DM Verity on top of it to do this measurement stuff, right?
There is support for doing that exactly that hash thing you described with S&P, well, and SEV on a direct boot. It's called like measured direct boot, and it's implemented in the AMD SEV OVMF firmware package.
It's in OVMF, right? But we don't support OVMF, right? We want to do direct kernel boot at that point.
Is direct boot the only way? Can you just boot an unmodified ISO, whatever it is called?
So we want to do non-direct kernel boots, like use like TD-shim or something like that in future, but as
Use
of now,
what you said?
TD-shim or something like that, so that it boots up the actual kernel and move all these hashes in a file instead of measuring. We only measure TD-shim, and then TD-shim takes care of establishing the root of trust.
Yeah, okay. So an ISO, as in you don't have access to the kernel at all then, or initRD? Like
Yeah, we don't do currently ISO boots or any other formats, right? Yeah.
But you
We
plan to?
can,
Yeah,
yes.
okay.
So real quick, going back to the boot hashing thing. So yes, the PSP is slow, right? You could imagine if you have a two-stage loader process where you load a minimal shim that is responsible for measuring the rest of whatever you're loading, whether that's QEMU firmware, kernel, initRD, that's the strategy you want to go towards because the PSP is slow.
Advertising here. We are going to talk about exactly that problem at KVM Forum second day, if you guys are there, in our presentation on how to bring your own firmware to VMs so that you can actually update all of that and have super fast reboot even with an ISO into your own launch measurement.
Looking forward to it.
Going back to a different topic, did you have to modify KVM at all in order to support running CVMs as a nested L1 hypervisor?
Yes, there were patches to modify KVM. I think one of my colleagues, like Jeremy, is working on upstreaming all those patches as well.
That's what I was going to ask, when those are coming.
What is it about TD-shim that specifically that makes it so you can't just use the hashed values that you're expecting once you transfer control over to TD-shim, and so that you could just hash in that trusted environment, you could just check what you're loading and against the hash values that are recorded into the image? Why can't that work with TD-shim?
It can work with TD-shim. I'm just saying that we don't have support for TD-shim. So TD-shim does not support SNP guess at the point. So it requires a lot of love to implement support for it.
So, maybe I misheard because I thought somebody had offered that approach, and you said that TD-shim was the reason you couldn't pursue that. So if that's not the case,
we don't implement TD-shim as of now, so we cannot move away to that approach right away. We're just using IGVM direct kernel boot to do all this stuff. Okay, then thank you.
Thank you. And by the way, just because we are moving on doesn't mean the discussions cannot continue in the hallway. Why don't we actually get all of you guys a bit closer to the mic, because there are a bunch of people I know who will be involved in the discussion quite a bit. Samuel, do you want to come up closer? And there's Alexi. I saw Alexi somewhere here. Alexi?
Not so much closer, but facing the mic always.
What? Yes. Hello, hi. My name is Suzuki, and this is a combined presentation between myself, Samuel, Alexi, and Dan. So I'll quickly rush through the 10-minute slot I have got. I'll be talking about the assignment of devices into realms and some of the issues that we have. Right, so a little bit about the CCA. It's an extension to the existing 1.0 architecture. The support patches are in the list. And the 1.1 update brings in a lot of features, including planes that my colleague Derek talked about earlier, and device assignment along with other features. So talk more about the device assignment aspect. So in this case, the RMM takes the role of the trusted security manager, which means it talks to the device and establishes the SPDM. All of this communication with the device is passed through the non-secure host, Linux KVM, and the mechanism is using the realm management interface, which the host can use to talk to the RMM. All the data passes through shared buffer, and secure SPDM guarantees the protection. So, and there is an interface between the guest, the realm guest, and the host to get certain information like cached certificates and measurements that realm can then verify with the RMM who keeps the digest. So that's how you verify the certificates and stuff. Yeah, I think that's pretty much it. And we can also support platform devices where you may not have actually the SPDM certificate as such. They are attested via the platform attestation report. There is a slide with all of the device assignment flow uploaded into the talks page. So I'm not covering all of that today. Right, and here's the interesting bit here now. When you have a device in the Trusty run state, it generates the T equal to 1 transactions, and on ARM CCA, the T bit decides what is the transaction state, whether it is non-secure or whether it's in the realm world. So when you have a T bit 1 transaction, it comes to the realm world, and all of these transactions has to be translated. If you're using an IOMMU, it has to be translated on the secure side of the IOMMU. T equal to 0 transactions goes to the non-secure world, which is completely under the control of the Linux host and hypervisor. The realm side world of the SMMU, it's under the control of the RMM. Now, as you can see, if the device starts using a stage 1 translation to talk to to access the realm memory, it needs to have a stage 1 translation that needs to be, the realm needs an access to the SMMU so that it can configure the stage 1 translation. That needs to be emulated by the RMM for the realm world transactions. Similarly, non-secure can be emulated by the hypervisor. And before we go into the problem, I just wanted to introduce some technical details of how it works today for the realms. So a realm sees its PA space, it's a single space, but technically on ARM CCA, it is split into 2 different halves. The lower half is the protected half, and the upper half is unprotected. Any access to the unprotected half, if you have a device, say, in MMIO region, in the unprotected, if you have an MMIO region, it could be either unprotected or protected, and the guest can detect this, whether this is a protected or unprotected, and at runtime, talking to the RMM. Any access to the unprotected IPA goes to the hypervisor through the RMM, so RMM can see this, but it doesn't do anything with it. It leaves to the hypervisor to service it. Anything that is in the protected space, it's handled by the RMM, and it can service it, and it's completely protected. The data doesn't leave the realm world. So with CCA 1.0, we don't have any devices in the realm world emulated by the RMM, but with 1.1, we'll have SMMU instance that the realm may need to use for stage 1 translations.
You mean private mode devices emulated in the RMM?
Private mode, there could be private mode devices. For example, a GIC interface could be emulated in the realm world. It may not be necessarily RMM. It could be one of the privileged planes like the Paravisor earlier we talked about. Right. So this is how it looks like when you have a non-secure device that accesses the memory. So the realm needs to set up stage 1 translation page tables for the device in the shared pages. And it sees an unprotected SMMU instance, and it maps it as such, and then all of these accesses go to the hypervisor. This is all good, but then when you turn this into the TDISP run state, suddenly the realm needs to use protected SMMU instance, because that's the only thing that the RMM can see, and then RMM needs to kind of configure them. So this is what it should look like when you have the device in the TDISP run state. The SMMU is emulated by RMM, and then any transaction that comes from the hardware, it checks whether it's, if it's in the run state, and if the T is 1, all of them goes through the realm SMMU, physical SMMU. Any T equals 0 transactions like MSI accesses, it comes to the non-secure SMMU, and it can go to the hypervisor. In that case, the realm doesn't need to even know that there is a SMMU in the non-secure world, because it doesn't have to worry about it. But it's all, the host can manage a stage 2 translation, and it knows the stage 2 translation for IPA to PA translation, so it doesn't matter. Now, so when you do this translation from the shared mode to protected mode, what do we do if the realm it knows about the stage 1 translations? It suddenly needs to switch the SMMU that it uses, or should we, how do we solve this problem of having 2 SMMU instances depending on which mode the device is in? So there are some possible solutions. One is, let's say that the SMMU is always in the protected space, and the RMM will always emulate it, and it can then pass on the information to the non-secure hypervisor if the device is in the untrusted state. If it's in the shared state, send everything to the vSMMU, and the hypervisor can emulate it. But this has a problem that all the realm world accesses are visible to the, all the SMMU interactions are visible to the hypervisor, which is not that bad because the device is anyway in the shared state. And this has to be done specific to the device, because there could be other devices under this protected SMMU. So the other option, so sorry. So just to complete that, when the device turns into the run state, RMM can stop sending the information back to the hypervisor. So this is fine. But the fundamental principle of the RMM, the host cannot see the realm accesses is broken. So which is the problem there. The other option is provide 2 SMMU instances to the guest, and it can be contained in a wrapper driver, and then the wrapper driver can decide, or based on the state of the device, you program the appropriate SMMU so that you get accesses going to the non-secure vSMMU, and then everything works. Or the other option is you're kind of breaking one of the other principles where a device is either protected or shared. Here you say that you have 2 SMMU instances. One is protected and one is shared, but they are exactly on the same alias on the other side, which was not the case earlier. So we could use one of that, where the realm has to program both of them, saying that it's controlled by 2 SMMUs. So any thoughts on the proposal? Yes, please.
For the unprotected, do you just want to use Virtio IMMU maybe? Does this help?
Sorry, I didn't get you.
For the unprotected, do you want to use Virtio IMMU maybe? Does this help?
Even
if you want to actually have the IOMMU running, you want to run it in nested mode, and you want all the acceleration. Like, you don't want to fall back to VirtIO IOMMU.
So again, the problem still remains, right? You have one device and two SMMUs, and if that's the case, why not use a emulation SMMU, right? You could.
But I feel like the simpler answer is that we don't actually really need translation available if you have it in t equals 0. Is that okay?
Is that okay? That's the other question. Yes. If that's acceptable, yeah, we're fine.
I mean, it's sort of ugly in the driver to.
And second question is, so like if you have two IMMUs and then you have to somehow make sure that the correct one is used for the correct device, and all this authentication thing has to also verify that in some way.
Yeah, so we can verify the SMMU aspects. The realm can actually talk to the RMM and make sure that at least the protected SMMU is what it expects. That's fine, but the problem is, or do we rely on the guest to say, when you transfer this device from shared mode to the protected mode, you do all the work, or the driver do all the work of, copying all of these shared stage 1 translations over to the protected SMMU instance.
One on the bridge.
Yeah, you can ask your question, Goran. Yeah.
Yeah. So I may have missed this, but I'm wondering, what are the use cases for a realm to want to talk to a device in both shared and private modes?
No, the problem is when
the same device.
Yeah, it's not going to be in the same. I mean, it's not going to be at the same time, but you may start a device in the shared mode, and you would have programmed some things into the device, like, oh, here are my translations, and you can share this. And afterwards, you may say that, no, I'm going to make you trusted now, and then what do we do about the translations that we passed on to the device? Do we?
That's what I'm struggling to see. Why would you do that? Why would you not just wait until you get the trusted device?
Yeah, I mean, but I would expect that would be a violent operation, because like DMA API is not ready for devices to have. So like when you want to go from shared to private, it's almost a hot plug. You drop everything and come back up in the private world with no shared mappings anymore.
Right. Okay.
So your question, some hardware has some interesting design decisions where you need to touch the device in the non-secure mode to even get to the secure mode. I'm not sure. And I agree with Dan, right? Like changing the way the IOMMU is allowed to work while the driver is bound, and changing what you want to do with the DMA API, it's not reasonable.
You might get there, but not.
Yeah, so I kind of like the idea that, at least on ARM hardware, at least for this generation, if you're in t equals 0 and you have a driver bound, then you're in identity mapping mode. And you're just stuck there, and you can't leave. And you can't use any advanced features. You don't get passive, you don't get SVA, you don't get any stuff. It's just like this stupid, very simple IOMMU that's pass-through only.
Yeah.
And when you get yourself into t equals 1 mode, it stays pass-through only. So you don't get any, there's no disruption to the driver. And then somehow you have to unbind and rebind your driver to switch it into fully operating mode with potentially a non-identity translation, although I suspect that's not the use case. But I don't know. It sounds complicated. Honestly, I hope you guys fix this in a future version and allow the secure IOMMU to process t equals 1 or t equals 0 with the secure copies of all the secure page tables, because that makes a lot more sense. That's what AMD is doing. I don't know what Intel is doing, but
I can certainly take the feedback.
Oh yeah.
So there's a question on the chat from Guren, and he asks, she asks, when t equal 1, is there any limitation for using ATS?
I don't think so. We have the protected SMMU. As long as we expose the protected SMMU, it should all work. But there are certain other requirements, like you need have pages pinned and whatnot. Yeah. I'm not sure if I'm eating into other people's time slots, so please feel free to come in and, you know.
This is kind of more of a question for general Linux cross-vendor things. Does T equals 0 traffic go over IDE?
I don't think so.
Okay, it depends.
Point out, we do have devices that will have at the both time TBTGL0 and TBTGL1
Okay.
when they're in run mode.
Well, you want to do it concurrently?
Yes.
You can't do it. No.
There you can.
No, you can't. Not
Well,
what we're setting up. Not on ARM, because they have two separate translations.
Yeah. So I understand his problem on the hardware side, but I just want to point out that we do have devices like that.
And in both modes, you would need stage 1 translations. I mean, do you need stage 1 translations in the shared mode?
Yep.
Jerome, I have no idea how we'll make that work in Linux, especially with this ARM problem where you have different translations for T equals 1 and T equals 0. Like, it makes sense on something like AMD where, yeah, sure, you can send whatever you want and it's the same translation, always works out. But here, like, Linux will need to actively block those kinds of devices from working. I don't know how we're going to do that. I'm sad that people are doing that. Please don't do that.
Right. Okay. Yeah, that's all I had. As I said, the device assignment flow, complete flow, is available on the slide on the site. Thank you.
Right. So I'm Samuel. I work for Revos, and together with Jiwen Yao from Intel, we're working on the RISC-V specification for computational computing I/O called the CoV I/O. It's a specification that depends on a few other specs. One of them is CoV, which is a computational computing specification for RISC-V. It also depends on H extension, which is the virtualization one, obviously. And another one, which is SMMTT, which is secure tables for RISC-V. So I'm going to talk about CoV I/O just to be clear. This is not non-ratified specification, so it's still being worked on. Anyone is free to contribute to it. Anyone is free to comment or change it. So please. So that's the high-level picture for CoV I/O, and I think one of the things I want to talk about during the few slides that I have is highlighting the fact that proposed ABIs for CoV I/O actually match pretty well what Alexa is building for TDS report in the kernel. So this is a fairly loaded diagram, but I think the most important ones are the green boxes, if you can see that, which are describing the flow between the host and the TSM, and then between the guest and the TSM. And we see that the host is basically going to request the TSM to connect to the device. Then it's going to bind a specific TDI into a VM, a TVM, a trusted VM. And eventually, there's a flow going down from the guest into the TSM for the TVM to say, yes, I accepted this device into my TCV. And this maps fairly well what Alexa is proposing in its RT. I think it's the last one is not called start interface, but it's a validate interface from Alexa. So just want to highlight this at least once. That this seems that it's something that's going to work with the proposed approach upstream. So you have two different interfaces with CoV I/O, the guest ABI and the host ABI, and those ABIs are part of the high-level confidential computing ABI, the CoV ABI itself. We're integrating into the generic confidential computing. Oh, okay. So a few more details on this, and again, describe the flow and how things would work with the CoVIO. A few prerequisites. The TSM owns the SPDM session, so the SPDM session that is established between the host, the physical host, and the device is driven and owned by the TSM, not the host VMM, obviously. And the TSM is going to manage the TDs and the IDE keys. So the TSM is going to own the IDE keys for the PCIe IDE session as well. It also manages the DMA and MMIO mappings. I think all of this maps pretty well what other architectures are doing, and basically what the patch set is trying to implement on top. On the other hand, the host VMM owns the physical device, so it's free to do whatever it wants with the physical device, which is what TDSP is here for. It initiates the SPDM session establishment, so it talks into the TSM to ask the TSM to establish the SPDM session. And then from there, the TSM owns the SPDM session. And to do that, the specific CoVIO ABI is called connect device. So it's from the host VMM into the TSM, asking the TSM to establish the SPDM session. Then if that is successful, the host VMM is then responsible for binding a specific virtual function of the device into the VMM, into the TVM, sorry, the Trusted VM, through the bind interface API. And this is what I also want to talk about in the next slide. The last step, which is basically for the guest to accept, explicitly accept the TDI into its TCVM. So there's a guest to TSM ABI for this. Oh, sorry. Okay, so the one thing I want to talk about, which is not we haven't talked about that a lot yet, is device verification. We've at Lucas PCI authentication buff, we talked about a lot about PCI devices authentication. That's not what I want to talk about here. I want to talk about verifying, attesting to the device. So authenticating the device is something that allows you to tell you that this is a genuine Samsung, whatever, Western Digital device. What we're talking about here is for the TVM to say, okay, what does this device look like? What is it running? What's its state? Which firmware stack it's running, and so on. And the PCI spec explicitly says the TVM should be responsible for verifying the device, doing the remote attestation or local attestation, doesn't really matter, but doing the attestation to the device before accepting the device into its TCB. So here we basically are saying, and the proposal that we want to maybe discuss is a proposal for a split kernel user space architecture where the kernel would basically offload the entire verification of the device to user space. So we have this Trusty device manager, whatever you want to call it, as a user space component, as a helper for the device, for the kernel to say, okay, this device is authenticated. I know it's a genuine device. Now I want to verify that it's something that applies to the policies that user space is describing. So user space is going to say, I want firmware version 1, 2, 3, and I want this device running in non-debug state, for example. It's a completely user space defined policy, and the kernel would just call into this user space component to run all this verification remotely, locally, doesn't matter. But the kernel eventually gets a reply from user space saying, okay, this actually complies with our policies. That we, as the guest owner, have defined these policies, and this device complies with it. So you can go ahead and probe this device and start allowing for running DMA transactions. Before the user space gives that answer to the kernel, we should not let the device run any DMA transaction into the private memory of this TVM. So that is a proposal. That's a component that we have to define, and it basically aligns pretty well with what's proposed for the SPDM patch set, except that we're lacking the measurement interfaces. But also, I think in the SPDM patches, there was a discussion about not binding the device if it's not authenticated. I think we want to extend that to not binding the device if it's not verified, if we don't get this verification approval from user space into the kernel.
But that's just another user space policy. I mean, like if user space is doing attestation, user space can decide to bind or not. We shouldn't be putting that policy in the kernel.
Yeah, correct. I agree. Yes,
Okay,
definitely. But we shouldn't let the kernel decide make that decision without a user space actually telling the kernel if it's a trustworthy device. Yeah.
Yeah. So I would like to know what would it be possible, or would it work for you to use NetLink?
Yeah.
Or I'm
definitely.
not jumping ahead. Is then the next slide?
No. It's a good point. Yeah. That's why we were telling you at you about that SysFS or NetLink. I mean, in practice, we're not going to run OpenSSL directly. This is a user space component that's going to talk into this interface. And NetLink is certainly more flexible than SysFS. So I think we would prefer to have a NetLink API as opposed to.
Okay, I'm wondering. So how would the user space component in the guest, what it's talking to? Where does the NetLink connection end?
The NetLink connection ends in the kernel.
Host kernel or guest kernel?
Guest kernel.
Okay.
So the guest kernel would be expected to run your SPDM patches and so on. I think we have 5 minutes left, so maybe I can take a question and then let Alex say. I don't want to.
We talked about Paravisors earlier today.
Yes.
Would it be acceptable for, I mean, your interpretation of the spec, if that manager was in the Paravisor and then just simply presenting it back to the guest?
Yeah, I think it's in the HCL talk. I think the Paravisor would be running this Trusty Device Manager. Legacy VMs wouldn't know anything about TDSP.
Yeah. So do you see that as a preferred approach, other than trying to do that in the guest?
Definitely. In the Paravisor case, I think the reasonable approach is to run this Trusty Device Manager in the Paravisor and implement all the verification policies in the Paravisor. You can't expect the legacy VMs to know anything about that thing.
Yeah, so I mean, I generally agree with this, right? We don't want to do the remote attestation, all that stuff in the kernel. But I'm a little bit confused on, because you said a few different things about we can't allow DMA into private memory until the device has been approved, but we could allow DMA into shared memory. Is that something that you plan to support? Because I think we should.
I think, yeah, I agree with that. I think.
Okay, so then I think that has to be a requirement of the scheme. And then after that point, you might need to reset the device in order to get back to start DMAing in a private memory, right?
Why would we need to reset?
Or at least or reload the driver or something like that.
Yeah. Yes.
Okay.
Yep.
Right.
Okay. Alexa is next. Something I didn't touch upon is device attestation and firmware update, which is another can of worms. So sorry about that.
Yeah, I have that working for AMD on TIO. By now, everyone knows by now how it works. The spec was out for a year, patch is out for like 4 months. In short words, we do things as we usually do, and we have IoT VM for ages. We just added a few bits in RMP, a few bits in IMMU. Picture is simple. On this picture, PSP, VM, and device addressed. Host is not, and everything happens via host. And what I wanted to ask you, now we do plumbing, next incremental step, how we implement things. Well, next respin of the patches. So my understanding is that so far we agreed on dev connect, dev disconnect, which is kind of sort of the persistent setup, which enables IDE between device and the host, which is PCI encryption. And in AMD, dev connect enables SPDM, secure SPDM, IDE does a little bit of TDISP. So if you wanted just IDE, this is not going to work. If you wanted just CMA, Lucas's stuff works just fine. Doesn't need any of PSP. Do we need any finer dev connect, which would only stop at IDE and not touch TDISP? Do we? Don't we? Now, next thing we need to decide on is TDI bind. When you bind virtual past function TDI to virtual machine,
But aren't there questions on how IOMMP UFD is connecting to guest MFD, is connecting to VFIO?
API issue, which is not really big. Just teach IMMU about guest MFD. Should be straightforward. Since everyone agreed on that, let's just do this. That's an easy bit. Not easy bit is I'd be interested in separate lock and run state. How do we do bind? Because it was proposed that we do bind prepare step first, so we teach KVM, VFIO, whatever about this connection, but we don't do actual binding till request comes. And right now, my request comes when guest starts, detects the device, sees its TIO, PCI capability, then it goes and asks BSP about the information of this device. So it gets to KVM sees its TIO request, binds the device to virtual function automatically, then it goes to BSP, returns information, certificates, measurements, all that, and guest looks at all this and decides if it likes it or not, and then it enables device to operate securely.
Sorry, one question. Regarding the binding communication between GMM and VFIO and IMMUFD, are you planning to add IMMU notifiers that could allow GMM to invalidate IMMU mappings?
Have to.
So if you're relying on GMM to supply PFNs for IMMU mappings, then if GMM removes those PFNs, it has to notify IMMU, just like KVM MMU, to remove those mappings.
Right.
So yeah, you're easier.
Now I'm using page stage change events in QEMU. Happens.
Sorry?
Now I'm using page state change events. So when this happens and page moves from private to shared and map it from private.
No, it's so what if GMM decides to remove release private memory?
Why would it do it? Because someone asked to make some page shared, right?
If that could be at runtime, so basically user space is free to remove GMM, right? User space can just close the file and remove.
Okay, then user space can unmap stuff because it's the same
So-
QEMU which is removing GMM.
So you're relying on user space to remove IMMU entries before you release the GMM file?
Yep.
Okay, that's the
I
problematic
didn't
part.
look that far as removing GMM file from a guest. Yeah, folios are referenced, so they cannot just go away.
I was just saying, even if user space tries to shoot itself in the foot and discard the pages, there's still going to be a reference on them because we have them mapped in the IOMMU.
So the yesterday's KVM microconference, I think we said that there will be no long-term ref counts on private memory. And that means you cannot rely on you cannot hold ref counts for mapping, pinning it to IMU. So basically you rely on GMM to pin the memory and not take the ref counts effectively.
Like maybe the GMM issue, like I think all the GMM stuff should be taken out of your patch series and done separately. Because there's a whole bunch of discussions with the KVM and negotiations with other people to make the GMM IOMMU connection work. And it just needs to be its own tiny little series that just does that. And I don't know the answers, right? Philosophically, you either prevent GMM from unmapping pages while they're in the IOMMU, or you notify the IOMMU to take them out before you move them out. I don't care. Pick a choice. Implement that. It doesn't, right? It's easy. I don't know the.
I'm just voting for the second choice when you notify IMMU.
Okay, he votes for notifiers. On the slide here, I think I said on the mailing list, like I imagine that most of this is in IOMMUFD. Has anyone come up with a reason why that shouldn't be the case? And I'm pretty sure like ARM needs it to be there, and I'm pretty sure you're going to need it there on AMD as well.
No, this goes to IOMMUFD.
Sorry?
This will go all to IOMMUFD. Yes.
Yeah, okay.
My superpower is ignorance, so I didn't know much about it.
Yeah, thank you. This sounds like a discussion you should definitely continue on the hallway track. Next session is about SoC peripheral T-Disp.
Hi, I'm David Hartley. I work for Qualcomm's System Security Architecture team. And I want to talk about using confidential compute with SoC peripherals. And by SoC peripherals, what I mean is peripherals that are on the same chip as the CPU, that are not connected externally via some PCIe link, and that are not even looking like PCIe peripherals on the chip. So they're not integrated endpoints in any way. They're just raw SoC peripherals. And these have some advantages. You can have on-chip security access controls that can help with isolation, that can ensure that your connections are secure. You can optimize things because you have more flexibility with the on-chip interfaces. You can have multiple DMA streams. You can connect with interfaces to other peripherals on the same chip. And you can make use of the scarce wired interrupts that are on the chip. But you have some disadvantages as well. Not having such a standard interface, you end up with less community support, obviously, for the software. So what we are considering and looking at is the idea of using the T-Disp protocol from PCIe outside of PCIe, extending it to cover these on-chip SoC peripherals, these platform devices, if you like. And if you look at it at a fairly high level, you have a lot of very similar components. A lot of on-chip systems have got some firmware controller that manages the rest of the subsystem. You can partition these subsystems in much the same way as you do virtual functions on a PCIe device. You have to have some sort of TEE security manager, some sort of TSM, to do the isolation of confidential VMs on the CPU. And you can have some sort of device security manager, which may be inside the peripheral or may be somewhere else on the SoC, that can perform the same functions to isolate those partitions for you and to assign them. What you don't need, you may not need SPDM between the TSM and the DSM, because you might have a secure channel on the SoC for doing that. You might be confident that you're talking to the right endpoints, so you might not need a certificate. You also won't need IDE, because you can use some on-chip access control architecture to protect the confidentiality and integrity of those paths. Also, if you look at the flows, they can be very similar as well. You could replicate the flow for the PCIe T-Disps with an SoC peripheral. You would have the same TSM operations, I believe. You would have the same T-Disp protocol messages back and forwards between the TSM and the DSM. Where things would be different is with the arguments in those operations and in those messages. So as I said, you might not need to set up an SPDM connection. You probably or almost definitely don't need to manage IDE keys. You may not need a peripheral certificate. You may have a certificate or an attestation token for the overall SoC that includes that peripheral. When you get down to having locked the device and you're starting for the guest to verify and validate that it's got the partition that it wanted, you will get some more information. You won't get the same information coming through. The description of the device is not the same as the description of a PCIe device. And so you will need those arguments to accommodate extra fields for things like extra DMA streams, which the guest will need to then validate. Just like validating the MMIO ranges for a PCIe device, you would need to validate that you got the DMA streams you wanted, you got the interrupts you wanted. You may even need to check that you got a collection of interdependent peripherals that you wanted. You may get them one at a time, but you want to have the whole collection. But I think from at least this high-level view, it looks like that's a feasible idea. And so what I really wanted to do at this conference, and I don't think we will have enough time to do it now, but in the hallway afterwards, I'd be very interested to talk to people to get feedback on whether this looks like a viable approach and what would be the best way to take it forward, both at the Linux guest and host interface side, as well as at this TDISP protocol, which is a PCIe protocol now. How would it be best to carry that forward and sort of ensure against further changes in the PCIe spec that will doubtless come as well. So thanks very much. I hope I've kept to the 8 minutes.
So TDISP happens to be part of the PCIe spec, but as we discussed, there's almost no PCIe dependencies from TDISP perspective. So there's no reason why you wouldn't be able to implement TDISP without on non-PCIe devices. I mean, but I think you still depend on having an SPDM or measurements exposed to the to user space, right?
Yes, in fact, one of the TDISP, there are not enough TDISP messages defined to get the measurements. You have to use an SPDM message to get the measurements.
Exactly.
But if you've got a secure connection, you may not need to set up an SPDM connection to send that message.
Yeah. So would it make sense to look at the SPDM patches and make them, or think about not making them PCIe specific? I understand you don't need SPDM, but what I mean is that having the same interface, regardless of a device being as PCIe and plus SPDM, whatever, or an integrated device like this one, it would have a uniform ABI.
Yeah, even though you don't need SPDM, but it might still be useful to be able to authenticate the device, because the device might have its own independent firmware and things like that.
Yeah. Pretend it's
So basically, I guess what we're saying, you still can use authenticated key exchange, so authenticated parts of SPDM, and then just take the measurements and don't use secure session part of SPDM, because SPDM allows to stop before secure session.
You may not even need the authentication.
So my very first thought when I saw the initial slides was like, why don't you just make your SoC expose these devices as PCI Express? And I just want to confirm my understanding of why. Because at the end of the day, like, it doesn't cost a lot to just put a couple of IP blocks in that effectively give you config space and you fake a few devices, right? The main rationale for this...
The platform, it can be, there are some very low-cost platforms where that extra cost is relevant.
I guess we are at time. All right.
Just because we're out of time doesn't mean the discussion ends right now.
Right. So I think this is going a little bit out of order. I should have probably gone before Samuel, but I'll give you guys a quick update on Cove. I'll try to dive a little bit, give you a quick dive into the ISA. Obviously, we don't have enough time to go over everything, but just give you a quick glimpse of like what's going on in the task group right now on the ISA and non-ISA sides. Atish obviously couldn't be here because of visa issues, so he might be online. So the quick TLDR is like there's an ISA spec in RISC-V to support the notion of confidential computing, but it's built in such a way to not just enable confidential compute, but the general notion of running isolated TCBs. Okay, that's sort of the property we want from the ISA. And that ISA extension is a PrivISA extension. So as you know, RISC-V has a PrivISA and non-PrivISA, pretty straightforward. There's a PrivISA extension called supervisor domains, so that you can run the ability, you can have the ability for software to instantiate separate supervisor domains. And I'll show you a picture to get that across. And that works with a bunch of other existing ratified extensions like the hypervisor extension, where we can use the notion of enabling the hypervisor support, hardware virtualization support in RISC-V. There is like a lot of work being done on the QEMU side to get the emulation of this ISA in place as it goes towards ratification. As Samuel clarified, a lot of these specs are in that early pre-ratification stage, but we're getting close to like the task group sort of completing their work. So they will sort of move into what is called a stable stage. And then after that, there's a public review stage where a lot of the open source discussion happens. The second part is the ratification of an ABI or a non-ISA spec, which is sort of where use cases come in, right? So the supervisor domains ISA extension, like I said, is completely agnostic of whether you're running confidential domains or just creating security service domains on RISC-V. The Cove ABI is a confidential VM extension ABI that sort of adds that non-ISA software aspect for the interfaces to Linux and KVM and other things. And that brings in that the confidential VM extension use case on RISC-V, and that is expected to use this supervisor domains ISA, right? So I'll sort of give you a quick glimpse into the ISA in 5 minutes. So as you know, like this is sort of a quick picture of like the privilege level supported in RISC-V along with the hypervisor extension shown on the right, which essentially gives you additional controls in the supervisor mode to be able to run hardware virtualized guests on top of RISC-V. And essentially what supervisor domains does is keeps the same priv ISA, so that software that's written to run within supervisor mode, user mode is largely unmodified, right? Modular some of the supervisor mode enlightenments we talk about like with other architectures, but it gives you that sort of horizontal isolation on the platform, right? So that you can essentially create one or more supervisor domain contexts, right, which usages can use for various different things, right? And what we sort of identified is a set of priv ISA extensions so that we can enable this notion of having parallel supervisor domain contexts running, because this requires a proper way to do scalable memory isolation across the platform, which RISC-V previously only had physical memory registers to do static physical memory isolation, and also requires capabilities to work with the RISC-V IOMMU, which was recently ratified, right, as well as do secure interrupts across these supervisor domains. So there's a set of extensions related to supervisor domains. Again, I'm going to give you a quick glimpse. The specs are all online. They are, like I said, in the review phase right now. So supervisor domain essentially adds a memory tracking table, right, which gives us this scalable physical memory isolation at different page sizes. It nicely composes with the SV architecture of RISC-V, so that if you have first level paging or second level paging turned on, the memory tracking table will work with that, right, and sort of give you the ability to do scalable physical memory isolation across domains. It also gives you the ability to use new fence instructions, so that when you're tagging things for a particular supervisor domains in the TLB, you have the ability to perform fencing. These come in use, obviously, when we are doing private to shared translations and things like that, again, which is specific to a particular use case, or you can go with a very static allocation of physical memory isolation. So this is the SMMTT extension. If folks are familiar with the terminology in RISC-V, S stands for supervisor, the next M is M mode, and then the memory tracking table, right? So there's a nomenclature for all these ISA extensions. So this is sort of a quick view into how the table structure is set up. It's very much biased towards large page sizes and really compacting the permissions for physical memory, so that you can have read, write, execute permissions on a per page basis, and you can choose whatever page sizes your architecture supports, right? The other extension to kind of give a very clean mapping both from the IO side and the hard side or the CPU side for RISC-V is called an IOMTT. So as I said earlier, I'm not showing you the picture of the IOMMU that's already ratified in RISC-V, but it supports the notion of device context tables and passwords and things like that people here are generally familiar with. What we are adding here is essentially the additional set of minor extensions we need, so that when supervisor domains are active and an IOMMU is assigned to a particular supervisor domain, the access control is provided through the MTT structures. You essentially need an extension called an IOMTT that can take a device request coming in on the fabric, let's take PCIe, let's take a device request coming in with RID, it can be mapped to a corresponding supervisor domain, and that will allow the hardware request to find the corresponding MTT and perform the translation, right? So just want to give you a feel for, how the mapping is done both from the IO side accesses and the hard side accesses. I won't touch upon this since we don't have time. The gist of this slide is like, there is a advanced interrupt architecture spec that's ratified in RISC-V that gives you the ability to over-provision interrupt files, whether you're using supervisor mode or supervisor with hypervisor mode, right? And this extension in the supervisor domain spec is to essentially allow M mode to separate out supervisor domain interrupt controllers and assign them to supervisor domains, but through these new notifications, still retain the control to essentially get control on the platform when an interrupt comes in for a supervisor domain that may not be scheduled, right? So this is very akin to, if you're familiar with the flows like posted interrupts and things like that, where you have a notification vector, you have the ability to essentially get a notification vector into the root domain, and then it can schedule whatever supervisor domain it wants to schedule, right? So with that, I'll stop here. There is actually a long presentation that we did this week at the beginning in the Linux Security Summit for people who want like a lot more of the gory details on the ABI and the ISO mechanism. I would encourage feedback on that as we go forward towards ratification. So.
Thank you, Ravi. And with that, we're on to our last talk for this session.
Thank goodness. Yeah, okay, bad news, guys, but all of you are probably going to have to do attestation at some point. Fortunately, we have a project called Trusty that Claudia and I are going to talk about a bit, which will hopefully help you with this. Claudia and I are from IBM Research, and Chris and Natish and Daniele. Similarly, they couldn't be here, but you get us. So we're going to attempt to cram all these things into this discussion, but please feel free to stop me or slow me down, ask questions, but let's make sure we get to Claudio's topics as well. First, a little bit of a reintroduction to Trusty. Most of you probably already have heard about this project already because Samuel talked about it last year at KVM Forum. Andy talked about it the year before last, at LPC. But back in the day, it was known as KBS, or Confidential Containers KBS, Coco KBS, something like that. Now we have this name Trusty. We haven't actually renamed anything here, but Trusty refers to the collection of a couple of different components, of which the KBS is one. So Trusty is kind of your complete attestation thing. This diagram hopefully lays it out. Trusty consists of the KBS, the Key Broker Service. This is the relying party in the RATS parlance. It also has an attestation service. This is the verifier. It also has an RVPS, which is the Reference Value Provider Service. This keeps track of your golden measurements. It also has a client that allows you to provision this stuff. And then you can see we have the guest side of things as well. There's a couple different ways to use this from the guest. In confidential containers, we have an attestation agent and a confidential data hub. But you can also have a much simpler KBS client, which we provide you, that allows you to just get resources into attestations. We have a whole bunch of platforms that were supported, I think 8 at the moment, and hopefully more coming soon. You can see there's an interesting mix between actual hardware platforms and some clouds that implement their hardware in a certain way, or that implement attestation flows in a certain way. Actually, those Azure ones are connected to this HCL thing that we talked about earlier. One thing to note, I mentioned that this is sort of connected to confidential containers. It's been developed in that community, but this, from day one, was intended to be a generic attestation solution. So truly, I wanted to work with everything that everybody here is doing, and if you think that's not the case, you should let us know. One final thing is a stat from the project. We have a PR response time on average of a little more than 5 hours. Same thing for issues. And we merge a lot of PRs kind of quickly, too. So we like contributions. Come and talk, and you will get responded to. I don't know how that compares to your whatever projects you're in, but I think it's not a bad stat. So the last piece of the introduction is that this whole thing is based around the KBS protocol, and this is the protocol that we use to establish a secure connection between the guest and the KBS, and we're going to use the secure connection to provide resources. And you can't read the thing anyway, so I won't go into the details, but basically there's a request, a challenge, an attestation, and a response. This sounds suspiciously similar to what we actually saw in Usama's presentation earlier with Attested TLS. The one thing I want to mention here that's kind of interesting is that this protocol does not specify anything about time, right? So all we know is that we need to do this to get a resource, but we don't say we need to do this at boot, or we need to do this then or later, or anything like that. And we'll come back to that a little bit because it has some interesting implications. Okay. That's the introduction done. Now I want to talk about some of the stuff that we're actually doing at the moment in the community to make this thing better. So one thing to mention first of all is that we have two policies in Trusty, and at first this might seem a little bit inconvenient. The policies are both OPA policies, Open Policy Agent, so you use the Rego language to write these things. Why do we have two? One of them is for the attestation service and one of them is for the KBS. And in particular, we're trying to actually capture two different things here. Your policy for the attestation service, this is the verifier, remember, should really capture what do we care about in the TCB, right? So it should kind of map onto how you're booting the guest, to how you're measuring the TCB, right? For instance, in confidential containers, we care about 4 things in the TCB, the initRD, the kernel command line, and the firmware, right? So if we write a policy over here for confidential containers, we're going to say, oh, okay, well, how do what values in the report, for instance, should I compare to which reference values coming from the RVPS? That captures your class of workload, right? Now, if you have a different workload that's not confidential containers, it's just a VM or something, you would probably have a slightly different policy to say, oh, I have a DM Verity hash that I care about or something like that. So I'm going to use, I'm gonna compare some other value from the report to some reference value. Okay, cool. The other policy is in the KBS, and this is all about when you should release different resources. So this is more about capturing your workload itself to say, okay, these secrets I care about, these secrets are associated with these ones should be released under this context or something like that. So we want to keep these things kind of separate. That's why we have two. Here's one of the things we're working on right now is replacing the token that goes between the two. So the output of the attestation service policy is our attestation token, and that is the input, part of the input to the policy in the KBS, right? At the moment, we have kind of a random token that just had some values we threw into it that seemed good, but we want to move to using the EAT/EAR tokens. And you might be familiar with this. There's a draft in this IETF phase to make a generic attestation token. And yeah, we want to adopt that. So we're in the process of doing this at the moment. And there's a couple of interesting things that have come up. One of them is that this process is not really going to give us full interoperability. In theory, if every verifier out there gave you an EAR token, you could then use these verifiers anywhere, right? You could use them with any KBS. But the details are a little bit more complicated than that because there are some things in these tokens that are specific to the platform that you're in. For instance, these tokens have a set of appraisals, right? So they can have like a CPU appraisal, which is a vector. By the way, this is the thing that's kind of the cool feature of this, is that this token has a vector in it that can tell you like, oh, here's the score. So it's not a binary like, oh, I passed or I failed the attestation. It's a score for a bunch of different aspects of your TCB, right? And it's hardware agnostic, but it's pretty specific. Anyway, so you have a vector of those vectors, and you need to key into this with a name of the submodule, and it might be something like CPU, or it might be something else. So actually, your policy does need to know a little bit about who is generating the thing. So it's not quite as generic as we'd like, and that's maybe something, if any of the IETF people are out there, that's something to maybe discuss. But it is going to give us some nice parameters, because it will allow us to separate even more these two different types of policies, right? Because currently, if you, well, forget about what's going on currently. Let's try and save some time. Basically, it will allow you to have a very specific but platform agnostic, generic information being conveyed from the attestation service to the KBS. Then you can write some policies about that. So anyway, to actually implement this, we are going to need to make it so that we can generate one of these tokens from Rego in the attestation service policy, and we're most likely going to do this by having expected outcomes, like expected terms that you can generate inside of your policy, and those will automatically be populated into the vector that I mentioned earlier. This will involve replacing pretty much every single one of our policies that we have and all the default values, but that'll be okay. So anyway, this is a big effort that's going on right now. Let me briefly tell you about two other things that we're working on some. First of all, runtime attestation. Okay, we do not consume runtime measurements, really, with Trusty, and this goes back to what I was saying earlier about how there's nothing about timing in the KBS protocol, right? That kind of entails that we need measurements that are not going to change over the course of the guest, because we tend to carry out this thing lazily, right? We do not do this policy, we do not do this protocol when you boot, we do it like when you first want a secret, right? This will also be kind of interesting when it comes to device support, right? Because most of the talk about device support, like what Samuel was mentioning earlier, is about doing something at bind time. Well, we don't really do that. We carry out our attestation later on, at whenever time. So we most likely are going to do some kind of re-authentication kind of thing. You still will need to do a like a bind time thing with a TDM or something like that, but then we will probably re-attest. We probably want to do this again so that we can give new nonsense to the devices and make sure the evidence is fresh, make sure that it's really connected to this challenge that came from the KBS, right? So we'll probably do it a second time. In general, I think it'll be relatively easy to generalize our current model where we basically have one CPU attester. We have a heuristic that detects, hey, you're on this platform, and it then triggers the attester for that. That will later automatically trigger the verifier in the attestation service for that. It should be relatively easy to generalize this to being, oh, I detected that I have this CPU and also this device and also this device and also this device. Run the attesters for all of them, bundle up all of the evidence, give it to the attestation service. That will run all the verifiers. That will get the claims. And like I said, we have a vector of vectors in the EAT token, so we will then be able to generate a vector for the trustworthiness of the CPU and all the devices. And then finally, your KBS policy will be able to say, okay, well, these secrets should only be released if I have a GPU or something like that. Okay, I think that's most of my part. Any questions on any of this front? If not, we can go to Claudio. Yeah.
Very strong. So I think one more slide back. So when you're talking, so you're having stated something like the measurement is expected to be the same. So what about all these things where the TCB actually changes because of Coco VM preserving updates and things like that? How do you treat this case?
Yeah. So your question is, okay, fine. If you depend on runtime measurement, what if the TCB actually changes? Yeah, we don't really count for that. So.
But what's your view on this? Do you plan to support this?
Well, yeah, we don't really have a plan to support runtime measurements. I think our view on this is that your guest VM should be designed in a way that the TCB is not going to change drastically between requesting the secret and doing something else, right? Which I think is not as controversial a statement as it might seem.
But basically you're saying that it's up to VM to handle.
Yeah. Well, at the time that you should boot the guest into a state that you are basically happy with for the duration of your workload.
I had the same question, but slightly different. So focusing on the device side, when do you imagine you should get the secret for the root file system in the boot up process? Would you like to see all of the attached confidential devices attested before that, or are you comfortable after? And does after, I don't know, how do you feel about this?
Yeah, well, so this ultimately is going to be a policy question that you would define in your policy, and Trusty itself is not going to be too opinionated about that. When you go to request your root key for your disk or whatever, you'll go to get that secret. That resource will have to go through some resource policy, and that policy will be able to say, oh, only give them this key if you have these devices or if you don't. Also, one other thing to your point, Elena, is that it is possible to do to use runtime attestation on top of this, right? So you can, people have talked about having the VTPM and the Paravisor. So Trusty is a good fit for injecting the initial state, right? And then maybe if you have some type of guest that is going to be really dynamic, that you do want to measure a whole lot, you can then use that. No, well, so we don't plan to consume that evidence, but I think Trusty could be very good for bootstrapping like a VTPM inside of a guest. Okay, we should go to Claudio.
So I had a quick question about this. So before we proceed, so you mentioned about the Trusty attestation protocol, and I would argue that it's not an attested TLS because it's not happening at the TLS layer. It's happening way above that, which is even above the HTTPS, right? So it's over HTTPS. And what stops, or what was the design? So I was honestly speaking, I was very excited, and in the CCC attestation SIG, we had a project that, okay, we will formally verify this Trusty attestation protocol. But then we came up with the problem when we analyzed it more deeply, we saw that, okay, so it has really no connection with the TLS. So it's not attested TLS, although it's a secure, attested secure channel, but I am really interested in knowing what design options actually led to not using attested TLS. When I say attested TLS, it should have some connection, either pre, intra, post. So it really does not have that because it's happening way above that, which is the over HTTPS layer. So can you explain a little bit more about the design option? Why
I'll do this yes, I'll quickly. So look, the KBS protocol is designed to work over an untrusted interface, including something like the proxy we talked about earlier, right? I mentioned that it looks kind of like the intra handshake, attested TLS. That's kind of our goal. You can also use the protocol over TLS, but it is very difficult to get the correct expected certificate into the guest to verify the KBS. At least it's very difficult to make sure that you have the right one. So yeah, it's designed to be over an untrusted channel, and we think that that is a feature. But honestly, I think we would maybe be open to transition the KBS protocol to happen over attested TLS. That's maybe something we should talk about.
Not really over, so I would say within that TLS or at least some connection to the TLS, pre-intra-post, some connection to the TLS should be there, so that provides you more guarantees like than authentication plus attestation. So I think I really have a feeling
short
that it's
answer,
very weak.
You can use the KBS protocol over TLS. I'm actually quite skeptical about what you gain from that in most cases for reasons that are kind of subtle. So you can use it over that or not. Yeah, let's get to the...
Okay, happy to discuss after.
So Tobin was talking in 1.5x. I have to talk on 2.5x. So basically, the idea is we are trying to provide some secure networking services in Trusty. And this is the PR we've been discussing. The idea is that, well, each confidential virtual machine, it has its own protections, the TE protections. When you send data over, sensitive data over the wire, you also need to protect that data and send it only to a trusted node. So basically, that's the idea. How to do that? We kind of giving some directions here, which is we try to protect that having a trusted. I put encrypted, but actually it's trusted overlay network, where we can create a trusted overlay network. For example, if the node 5 is not trusted, you don't trust it, although it can be a overlay network is not going to be part of your overlay network. And if there is for example, a link that you don't trust, maybe it's unencrypted, the overlay network will have it encrypted for you. And there are multiple, there are multiple frameworks or tools that you can use to encrypt. And Nebula is one of them. There is also the IPsec options. The IPsec doesn't have the features we've been discussing. And Nebula has one interesting thing. It has a lighthouse, and that lighthouse can control all the nodes that is part of your overlay network. And the idea, and it has support for, it happens in layer 3, and has support some of the protocols that are most interested on. And the idea is for Nebula is, well, Nebula doesn't support confidential virtual machines, so we need to figure out a way to integrate it. Yeah.
So the whole industry is moving towards zero trust, right? Which pushes all of these things way higher up the stack, so you don't just randomly have a network that could potentially leak data somewhere where you don't want to have it leaked. What makes you think it's a good idea to enable layer 3 network in such a setup?
I'm sorry, link what?
I would expect that confidential communication, which is what you're enabling here, right? Like confidential VMs that then communicate between each other and may need to exchange handshakes that say, yes, this is actually the right entity on the other side, that they would want to strengthen their security posture. And my understanding from the overall security community so far was that the higher up the stack you put that validation, the more secure it's considered, which is why we are in this world with zero trust. You put everything over the internet. You believe that everybody in between could intercept you, and so you don't even do things like secure networks. You just always do it on the application layer. But here you're enabling a networking stack to basically hide that fact from your application layer, right?
Yeah, sort of. But there is also this part of here with Nebula, there is this lighthouse. So you already know that the node you're talking to is trusted. It was attested. And also there is also some other stuff, such as some other things, such as DNS. If you need to talk to someone, and you could kind of benefit from this kind of lighthouses entity that is coordinating maintaining all this information for you, and you could have a hierarchical DNS and things like that.
Sure, and then one of your nodes happens to have a curl backend thing that just happens to give you random access into some local IP address range by accident, and your whole network is toast. While if you do it all on higher level application layers, you're naturally protected against that. So we usually try to design our networks these days by not enabling either way. Keep going.
You want unmodified application support.
You want authentication at the application layer to be trivial, right? You want to
completely. Because keep in mind, this is mainly happening for confidential containers. So we want to be able, someone has a totally normal workload, they don't change it at all, but now they're going over this encrypted network. So we want completely unmodified applications.
He keeps showing me the stop sign. I understand. I'm not a huge fan of the notion that you can lift and shift something into confidentiality that wasn't confidential before.
That's what we're trying to do. It ain't easy.
It's not going to work.
Let me ask just one quick question. Can I? Hopefully. So it's about, I'd like to see if you guys have any feedback on offloading encryption to the NIC. We have all these problems with, okay, the NIC can support attestation, but then is the NIC ready to, is it okay if we offload the encryption to the NIC? Does the NIC has all these separations, these isolations, and so on? Yeah, it does.
Okay. Since I have
it's
the
okay
microphone,
to offload encryption. Okay.
Since I have the microphone, I can give you a very simple answer to that question. If you run a confidential VMs with CFSMP and the likes, and you want to rely on that infrastructure, the whole purpose is to remove the cloud vendor from the equation. All cloud vendors these days use DPUs, which means they own the software stack. At least for us, that's completely the case. Some others do too, which means they cannot, by definition, be part of a TCP.
Okay.
They can if the NIC supports, for example, a confidential computing technology on the CPU side of the NIC, for example, CCA or any of these others, then there are ways to do it.
So here's a thought. There's lunch happening right now. You guys should be having lunch together and talking about it. But thank you very much for attending, and I hope this was a useful session.
Say hello to the crowd. For us to say hello, and then we can switch over to Kasim. And
closing the doors, so you're all trapped here now. Okay, welcome everyone to the Internet of Things and Embedded Micro Conference. We're excited to get together for this event. Before we get started, we want to give a shout out to our sponsors. We wouldn't be able to have this nice exposition space and without the support of all these, and especially Linux Foundation staff. They do a great job organizing things, and a lot of work goes into this conference. Just a little reminder, of course, we want everyone to have an educational time, but also harassment-free time here. So just be careful how you treat other people. Just be kind, and I think we'll all be in good shape. So with that, do we have any other introductions we want to make?
No, not really. I mean, just for people that have been here last time or something, so this is a bit of a move over from IoT only. So we are moving over a little bit from just an Internet of Things micro conference that we had before. Now we're teaming up here with Tim to actually get more embedded stuff in there, so just for the focus of the people. I mean, we had the agenda up before, so we have basically 3 or 4 different topic areas, I would say. The first one, until the break, will all be about boot time optimization and things like that. After that, we have like 2 sessions on connectivity, and then we have device tree overlay, and then we have another on MPU and MCU link. So that's basically how we structure that one here. If anyone is interested, there's the shared notes, so filling that out for you, for yourself, for your notes, for your employer, just for the community, that would be helpful. Jan is doing a lot of work on that, but it would be great if someone else can skim it as well and put in some opinions.
With that, we will move right into our first presenter, and this is going to be talking to us about productizing Linux boot time. So go ahead.
Yeah, I see a few faces from my previous session. So yeah, again, repeating the same line. So I bring only problems to plumbers, and I don't bring solutions here. And when I bring problems, when I return back, I always have some solutions in hand. So this idea came up, like Tim brought this, like we had initial, like in last plumbers, like we discussed some of these Linux boot time issues that we were facing when we were dealing with the end products that TI delivers to its customers. And then Tim asked me to run another follow-up session. So whatever problems and learnings we have seen in last 1 year, I thought I will summarize those things and share here. Some of these are already solved in some way, but they are not productized today. Productized, upstreamed, these are the gaps that we have today. So in a nutshell, if I have to say, boot time is not like how you hit to the prompt faster, right? That is not what is meant by boot time for us. Like, it's mainly what use cases you can cover while you are booting the software on any given SoC. Now, by use case, I mean like you might have hit the prompt within a second or maybe like 500 milliseconds. But after that, if you have nothing in your system to even play an audio, sound, or to show something on a display or run, give a CAN response or a network response, then that boot has no meaning, right? So how do we ensure that whatever boot we have done has some meaning or is meaningful? So the scope of this session is to come up with those areas where we have what we have dealt in last 1 year and see what problems and challenges we faced in those problem areas and see how we have resolved in some cases and where they are still open for us. So that's the intention of this. Now, when I talk about boot time, right, like there are some fixed functions which we cannot do much about it. They are all like if kernel boot has taken 500 millisecond or even 1 second, some of that like majority of that time has gone into executing fixed function, and that fixed function is because of your hardware limitation or your SoC limitation or your system limitation. Now, for example, instead of using OSPI for your flash access, if we have used 1-bit flash or 4-bit flash, the speed of that read is going to be slow anyways, right? And if you are not operating eMMC at a given rate, then your fetching of that image is going to be on a higher scale. Similarly, if you are authenticating the image, like what your secure accelerator is in your system and what type of mechanism you are following for secure boot, all those things play a very important role while defining your boot time optimization. So where is your image size, what is the size of the image, where is it located, how are you fetching it, how are you authenticating it, how are you decrypting it, authenticating it, and then loading it into DDR, how much time have you taken to initialize your DDR, and so all those, whether it is a 16-bit DDR or 32-bit DDR, all these things play a very significant role in defining your boot time. Now, these things are, as I said, system-specific things. So this is nothing to do with open source or kernel or bootloader, right? Like here we have to live with whatever system we have. We are enforcing, like in TI now we are taking boot time as very important topic. So when we are defining our new SoC, we initially think, now if you put this security accelerator, is that sufficient for me to get to the boot time of 1 millisecond or something, or 1 second or something. So 1 millisecond, I raised my bar on myself, I'm sorry, that is wrong. Remove from the record, 1 second, okay. So we have to deal with those things. So we are taking those measures when we are making our EVM, whether we should put OSPI or OSPI NOR or OSPI NAND, eMMC. Based on the applications, we make those systems thing. So this is the first problem, and solution here is like define your system in the right order, pick your right device, right peripherals, pick whatever clock rate, all such things matter here. The second problem, which is pretty much something which we do in combination with bootloader and kernel, right? These are something called early use cases. Now, we can't wait for kernel to boot to prompt and then play a tone or give some early logo on your display. Now these are called as early use cases, pretty common in automotive world, and also now we are seeing this being used in many embedded systems. So here what happens now, I turned on the power of the product, and immediately the expectation is to see if it is a display with head unit, a simple logo should come up as quickly as possible. A tone should be played if it has an audio device. An LED should glow, power LED should be visible, right? Now, these things you can do after the kernel boot, but then you are taking your system to 1 second to 2 seconds away. Now, if you want to do much earlier in the system, then you put all these functionality in your bootloader itself. So we maintain 2 bootloaders. One, we go with standard U-boot and try to do something in SPL and U-boot and then go into the kernel. We also have our own secondary bootloader, which is an RTOS-based application which tries to do things more faster compared to U-boot. But whatever we do in U-boot, the biggest problem that we have here is how do you notify kernel that I have already initialized the hardware. Now you don't reset the system. Now in bootloader, I already have Splash running, and then I showed a logo. Then the kernel takes over, and now kernel, if it resets the display subsystem, it will show a glitch or something on the system, right? When your audio, similarly with your audio or your connectivity interfaces, like if you have a network port or CAN or USB or something, you initially started giving responses from bootloader, and when you get into kernel, now you're resetting the interface, so you will see that interface going down and again coming up. Now there is no easy way to communicate from bootloader to kernel that these peripherals and interfaces are initialized. Now don't do anything or don't touch this or don't reinitialize things. Or if you are reinitializing again, like at what kilohertz will you reinitialize, and all those things matter. So this is one problem that we are seeing on how to communicate. Like on display, we have a mechanism with the simple frame buffer DT node, which can pass on this information that I have run a splash now, don't reconfigure it, and kernel can take care of it. But similar hooks are not available for networking and other systems. Now, if you play something in audio, that is a strange issue, right? Like if we, like what is the duration of the tone that you are playing? Now, if you are playing a tone for like minimum thing is like 1 or 2 seconds, right? Like you should, an audible tone is at least 1 or 2 seconds. Now, if you play 1 or 2 seconds tone, and if you leave it on a DMA or something, maybe that works. But if you are in a loop or something, that means you are delaying your boot time by 2 seconds. If you are holding the boot of kernel and not giving a parallel boot while your bootloader has finished audio tone playback. Now, this is another thing that we need to see, like how is it going to impact the boot time while your tone is being played from the bootloader itself.
Sorry, that's a question. Instead of communicating between U-boot and the kernel, wouldn't it be better to eliminate U-boot completely and just immediately go to the kernel?
We also do Falcon boot in many cases where SPL directly jumps to kernel and kernel takes over. Now, to do anything in kernel space, you need to come up with your own services, right? Like if you want to play an audio tone, now you cannot introduce that audio tone playback in the driver itself. Now it has to come from an application. Now you have to have your services running, ALSA running, then application kickstarting, and then that thread should run to play a tone.
Yeah, but my point is, I think it will be easier to have to implement a fast path initialization in the kernel than it is to have a stable interface between the U-boot and kernel to propagate driver state. Because the thing is, whatever you communicate between U-boot and the kernel will depend on the way that the driver is implemented in U-boot and the way that it's implemented in the kernel. And I think it's going to be horribly complicated to do this in a somewhat generic way.
So, just a preview of coming attractions. DT might not be the best interface to use because I'm trying to get rid of DT. That's controversial. We'll talk about that later. So if you do it with command line parameters, there's already a fair number of command line options that tweak behavior of drivers right at startup and reduce boot time. So I kind of wonder about that. What about boot config? Or, you know, there's that other mechanism for handing data into the kernel. So I think it'd be great to come up with some kind of standard for, you know, if a peripheral is already initialized, you know, somehow notify the driver. But you're right, we need standards for that.
There are multiple ways of doing it. I'm not denying that, right? Like you can eliminate U-boot, directly jump over SPL to kernel, do Falcon boot, and initialize your interfaces faster in the kernel. But then you are still limiting yourself. Like the performance in number that we get, like we need CAN response within 100 milliseconds. We need audio first chime within 500 milliseconds. We need camera, if you put in reverse gear and you want to start your camera within 1 second. So these are some of the requirements that we get as soon as you boot your product. Each product use cases are different, right? Like now, in order to meet that, you can start doing tweaks and tricks. It is possible, but it becomes like hacks instead of becoming something which you can carry in your software for long. It won't become a standard product offering in cases like these. This is one problem. Anyway, I will highlight all the problems, then we can definitely, I'll give more time to discuss these. So,
I have a question about Ethernet. So if you initialize the link in bootloader and pass it to the kernel, I understand that it saves the time, but actually there is no data transfer possible. I mean, there's package loss and so on. Why do you fake it?
we don't have to. Like there are some cases where we are requested to give early Ethernet, like where you want to start your response on network packets. Like you just have to say that my interface is alive. Like if you have if you have an audio interface connected over network, like if your peripherals are connected over network, or in car where the peripherals are connected over network, you have to initially give a response to a first packet. So you give response and after that you can continue your stack later as well. But this is only for an early response to your initial packets. The use case is only for early packet response.
Cat fellow. Anyway, okay.
So then there are some combo use cases. So what I explained initially was like how do you do early use cases. Now in early use case, how you do display plus audio together, or camera plus connectivity, or display plus connectivity kind of things. Now again, these things are like while you are playing your display logo, you also want to have your audio running in parallel, and you want to give like audio plus a tone and a logo together, right? Now if you want to do this in bootloader, again it becomes complicated because U-boot is not multi-threaded. So like I just pasted a link where Dengs said that. So you have to either start audio first and then start your display, or start display first and then start audio. Then both of these things you need to take it to kernel and continue processing later in the kernel in Linux world, right? Like so that becomes a second issue what we just described. So here the issue is like how do you do sequential things like one after the other. The second thing is how do you communicate to kernel that these peripherals are initialized. So this is combination of 1 and 2. The problem 4 is like when you have remote cores in your device where you have multiple DSPs or multiple microcontrollers which are used to do some kind of initialization. Now there is an MCU which is handling an ADC to read some sensor data or something. Now when you boot the device, the MCU is up first and it is starting, it is responding to some packets, or it is initializing the ADC and reading some sensor information, or it is initializing the camera and starting like collecting the initial frames, or it is like if it is a display cluster use case where you can initialize the display and show some initial telltales, like immediately it will show some telltales there, and then Linux boots on A core and it takes over the display and other peripherals. So in such use cases, again, like how can the remote core in this case is the MCUs and DSP, notify to the Linux kernel saying I have already initialized these peripherals, now you don't initialize it again, or if you initialize in the same order, right? So there are no standards for these things. The reason why I am bringing these topics here is while you are doing Linux boot optimization, these issues are addressed today in the industry, but by following all the tweaks and tricks without following a standard mechanism or a standard process. And what I have done, somebody might have done in a different way, and I don't know whether they have done it or not in the right order or something, or I might be wrong. Now how do we collaborate and how do we work together? So my fourth slide is mainly summarizing the issues that I just explained in last 4 slides. So basically the important aspect here is like if we have to discuss anything related to boot time and boot time optimizations and these things, what is the good and right channel for us to discuss these things or bring up these topics, right? Like as I said, if we go to networking mailing list or anything, then it becomes like more towards networking concepts, or you go into media, or you go into audio or display. They are very specific to those subsystems. Now the issue that we are dealing is like bootloader optimizations and then the frameworks, right? So where should we discuss these kind of boot time tips and tricks? One issue. Second thing, where do we host these topics that we have? Like if I have made a hack and I want to pass on this method what I have done in the kernel to optimize the boot time and still show a logo or play an audio or something, where do I host these things? Like, is there a project where we can host these tips and tricks which we can pass on and later fine tune it more? Like, maybe the initial step that I have taken is wrong, but I also want to review this with the community, and if there are better ways to do it, I want to learn and implement those things in our standard offering. That is one part. Second thing is on file systems, right? Like, file system also plays a very important role in boot time. Now, what should be the minimum file system that should be given for optimized boot time, and how that file system will scale later to cater to the end product needs? Like, if you start adding lot of services or lot of packages, lot of applications in your file system, the amount of time it would take to mount that and boot those services is going to take time, right? So in our case, what we have done, we have multiple Yocto wiki images. Like, when you build for a defined OE config, we actually give 5 different wiki images. Now, first is very thin wiki image. Then there is something which runs with Docker, something which is default, which is blown up with all the packages. So we have some basic default thin tiny kind of thing for different use cases and different sizes. So this is one thing which we have done, maybe not the right way to do, but this solves one of our purpose of dealing with boot time and solving issues related to file systems. So, and the other last item is like, how do we do test automation for these things, right? Like, today, like we were discussing, I was discussing with Tim, also brought this up, like in kernel CI, can we have a test to monitor the boot time of kernel? Like, and is it changing every release, like every RC? Is anything in the kernel impacting the boot time, right? And how do we see from version to version what is the boot time? Today we have RT tests for real-time cyclic tests are published, right? Similarly, can we have some standard test which actually gives the boot time with every RC or every major release kernel version, so that we know how much we are deviating on the boot time? And that is also challenging on us, like when we want to do display plus boot time, audio plus boot time, these things have to be automatically tested and results to be published. So this is all I had. I wanted to just share my experiences and the problems that we have faced and how we have solved in some form. But we have all this code on our GitHub repository today, which you can see and refer, and you can reach out to us. We can always share our documentation and the hacks that we have done. But if there is a collaborative project, then definitely I would like to participate and host all our code there to help the community.
Okay, so I actually have almost the same set of requests in terms of where do we do this stuff as you have. So is there any reason we can't use the Linux embedded mailing list? The actual kernel Linux embedded mailing list. It's a defunct list. Nobody's on it except every once in a while you get a support question from someone, but it's not being used for anything else. And I think this is exactly the type of discussion that should go on there. That means that we have to like stop ignoring that list and kind of get on if we were going to collaborate on some things. But that would be my suggestion for a mailing list. As far as a wiki, I'm going to put my stuff in, I have some tools that I've developed, and I'm going to put it on the eLinux wiki under the boot time topic. And then I am actually working on a layer, a meta layer for Yocto that I'm going to also put the tools in. But I don't know of any place where we're having a project. So I don't know if anyone has any, like.
Wiki is good place to start. At least we can give all the links for the for the patches that we are carrying in a particular repository. So yeah, if there is a wiki page, definitely I would like to participate and add those things. Meta layer will be very interesting. Like if you can share.
Yeah, but like it's going to be under. It's not going to be under like Sony's repo. It'll be like my personal repository. So it's not a very official place for such things. So I don't know. Any other comments?
Maybe you should select one of those use cases where you transfer an active device to the kernel from the bootloader and figure out a way to how to suggest such an interface and submit that to the relevant kernel subsystem and to the device tree maintainers probably, to see, to at least get the discussion started that there are these use cases and give a concrete example how that could be done.
We have done one for early splash screen. We have done those things, and the patches were also submitted, and we also have given the talk related to that in ELC and other places, like how we have implemented those things. Case by case basis, like we are working with the respective community and projects there.
So, okay, I have a comment.
Okay, if I might add some comments. In U-boot there is like the boot stage facility that you can pass some information regarding what has been achieved in which boot stage. So this is already there available. You can pass information between the SPL to U-boot, and then you would know which stage you pass. And the second comment, I don't know if it's still possible, but with the IMX, I remember that there was the information device tree that you can specify that this pin, for example, is already configured by the bootloader. If I remember correctly, it might change, but some time ago it was possible to specify in the NXP device tree that, okay, this IP block, this pin, whatever, is already configured by the bootloader. This was special flag, if I remember correctly. So that was solving the problem with the glitches on the display because you didn't reconfigure the pins, which caused the glitch, and also some networking, I think. Excuse me? That was downstream? No, it was in the mainline.
All right, before I send it back there, I just wanted to comment. Okay, so boot time is one of these things that I call systemic throughout the kernel, right? It's like real time or power management or size, system size. System size was really hard to kind of get an ecosystem around because you're removing code, so there's no maintainer until you hit the individual thing. But if you want to do some kind of systemic reduction of size, it's like there is no maintainer. And it's the same thing with boot time. There's no boot time maintainer in the kernel. And so that's, I think, one of the things that makes it a difficult proposition. So I think it's really good to try and get some kind of group together, even if it's informal, to work on this stuff and collaborate. So, and there was one.
So just for the record, you can kind of do that already in DRM for the display side of things. So it's not generic yet, but we have a plan for it because Intel is already kind of taking over a device that is running so that you can have flicker-free boot, sorry. So yeah, it's not generic, but it's doable, and we have a plan for it. So yeah, if you want to, it's something we can discuss some more, and yeah.
How much do we really care about cold boot these days and not like resuming quickly from suspend, right? Because like Tim, you mentioned two systemic problems are boot time and power management. Maybe we can combine some efforts there and actually work on them both. And I think a lot of these use cases, I mean, cars have really big batteries. I don't know that they really ever turn off, do they? I mean, maybe we should be looking at, I mean, obviously I know some of them do, but I mean, in a lot of use cases, I think we could be optimizing, working on suspend resume speed ups, and it could also have have similar benefits to like the use cases you're talking about, not from cold boot. So.
With Linux RT. So we have Linux RT plus power, so we need to solve both for this. I said we need to solve Linux RT and power because most of these use cases are running on RT Linux. So that's one thing that I was discussing with you yesterday, right? Like how do we solve RT Linux and power in some cases? So.
Okay, we got about 1 minute left, so time for maybe one more question.
Nice seeing you all. Thank you for staying around.
Okay, thanks. Hey. Now we'll turn the time over to Laura.
Hello, everyone. So, my name is Laura, I work at Collabora, and today I'm here to talk with you about boot time testing with Ftrace. And the reason I am trying to talk about this stuff is exactly to answer some of the questions that came up during the previous presentation. So why can't we have like a test in kernel CI or whatever CI to make sure that the boot time is good enough throughout the subsequent boots and it stays the same all the time? So at the moment, there's no case of tests available upstream, so we couldn't find anything really easily automatable, let's say. We have some utilities in the kernel tree, in the tools and script folder, but these are really meant for manual usage, so the results are really meant to be looked by human eyes, and these are really challenging to run in a CI or in a non-interactive environment. So let's look quickly at what we have available. There's a Perl script in the scripts folder that just converts the kernel output into an SVG and tracks all the timings. It is tracking just the init calls, and it has very little dependencies, but again, it produces an SVG, so that's pretty much impossible to have it automated easily. There's the bootgraph Python script, which is a little more complex. It generates an HTML output, and it both tracks the init calls, and it also has support for Ftrace. So you can track a little bit more with that, but the Ftrace is limited to a pre-configured configuration, and it uses function graph. So depending on the types of events that we want to track during the boot process, we may need some more flexibility than this. And again, HTML output, we cannot really put it into a CI and parse it easily. So what do we need in order to create a task for this? We need a way to track the time for some key boot events or functions. We have the kernel log, the timestamps, and we have Ftrace. So I feel like we have the ingredients that we need. We're just missing the actual test. We need one critical thing is like trying to identify what events we're interested in tracking. I feel like there's like a lot of different use cases in this, and what may work for us may not work for other use cases. So I feel like the main question I ask myself when looking into this is, what actually do I track? Do I track all the init calls? Do I choose a specific subset of critical events? But again, that might work on my use case, might not work on other use case. There's an upcoming presentation on boot phases. I think this is going to fit as a topic, so stick around to discuss this. So we try to come up with an automated boot time test with the goal of detecting regressions over time, so integrating the test in a CI and see if there's any slowdown in the boot process. Our hard requirement was to have an upstream test, so put it in the kernel tree. This limits us to the pre-init phase. We can track up to the init loading phase, but that's I think we can get pretty far with this as well. We wanted it to have minimal dependencies and little maintenance over time, as little as possible. And we wanted this test to be generic, so again, to work on many different platforms, many different use cases, and to be easily integratable in a CI environment. So what do we need to implement this test? We need a way to trace the key boot events. So again, we can use the kernel log or Ftrace. We need a parser to extract the timestamps. And we finally need a way to, some kind of mechanism to detect if there was a slowdown or not. So the only way I could think about this was to have some reference values. So just run a first pass on a known good kernel, a kernel that has good timings, and generate some reference values that you can then use for subsequent boots. Of course, this needs to be updated over time, but hopefully it's not that often, so the maintenance should be pretty small, I think. And we also need the user to provide the variance allowed between subsequent boots. This could either target the start of a certain function or the end of certain function, or the overall duration. So it could be just one value for all the events that we're tracking, or one value for each event. And again, I was not sure that like my use case would work for other use cases, so I'm here to talk about it, like to find a common ground. So I submitted a very basic proof of concept for this. It's an RFC state, and the approach for this is, it is an upstream case-level test. The approach is to configure ftrace once to track the timings for specific subset of events. Compare then the timestamps of your subsequent boot against some reference values that are generated in YAML file and provided to test. And then the test will just flag if there's any deviation beyond the specified delta. So I'll go quickly throughout this proposal. I would like some feedback on some of the implementation. So the first part of this test is a boot config file. This is to configure ftrace. I think this is a pretty flexible way of doing that because it avoids the user to have to configure the command line, so configure manually ftrace before the test. So there's this very simple boot config file that I used as a proof of concept, but it will eventually need to be populated a little bit more. You can just put some trace points. I just put some K-probes here, just as an example that worked for my proof of concept. And this file is shipped with the test. So what I would really like to do is try to populate this file with events that will work for many different platforms and use cases. Along with this boot config file, there's a config fragment that enables boot time tracing and is meant to also attach the previous boot config file to a kernel image. This is, again, a way to try and ship all the dependencies along with the test so that the test user doesn't have to do much manual work before running the test itself. There are other ways of using the boot config files. In this proposal, I decided to attach it to the kernel image. There are other ways of doing that. We can discuss alternatives. After there's also a script that generates the YAML file with the reference values. So this is a very simple script that just reads the trace file and dumps the timestamps into a YAML file. And again, this is supposed to be run just once once and updated every once in a while. You run it on a known good kernel, and it will spit out the timestamps on a YAML file that we can use for reference for the subsequent boots. And finally, there is a script that's the actual test. So you feed the YAML file with the reference values, and you provide delta that you would like to use for the test. In this example, I used 1 second. So what it will do, it will just read the trace file and compare the timestamps against the YAML file with the reference values and just flag the test as failed if any of the tracked events is taking more than expected. So in this example, I was able to pass on all the use cases, but in this other one, I got actually a failure. So we'll just spit out a failed test case if there is any difference, significant difference between the timestamp and the reference value. Being a case of test, I decided to use KTAB just for convenience. And I got some early feedback on this RFC from Shua. She asked me to look into the other tests available upstream to see if we can reuse them. I think Bootgraph is the one that's closer, that's doing the thing closer to what I'm trying to achieve. But in order to use that, we would need to add some machine-readable output. Could be JSON, could be YAML. And the timestamp parser might need some adjustments because, again, it's supposed to be used with a fixed ftrace configuration that might not fit all the use cases. So it's definitely doable, but I wanted to have some feedback before trying to touch the script and make it fit my use cases. So I hope this is visible. Yeah, it should be. I have a bunch of questions. I have more questions than answers on these tests. So the main thing I would like to discuss with you is like what events are you interested in tracking? When you're looking at boot time, I'm sure a lot of you do boot time testing. Are you looking at all the init calls? Are you looking at specific critical functions? because we can track both. And with this boot config file, we can put everything we want. It's pretty flexible, so we can configure ftrace however we want. But I'm not sure which is the right way here. And if we decide to track all the init calls, we're going to generate a lot of output. I don't think this is that relevant when we run the test in a CI, but if the user decides to run the test manually, we'll get a bunch of pass and fails and skips. It may be hard to read. One way of solving this might be to show just the failures, but as far as I know, the case of test is not really doing that, apart from a few exceptions. I would also like some thoughts on reusing bootgraph. I don't know if there were previous attempts on doing that, like making it easier to integrate this into a CI. If there was any other attempt, I'll be happy to discuss it before I try to do it myself. This test and other tests upstream use a reference file. And again, we talked about this in the previous presentation as well. We need to figure out a way to where to store all these files. This will be useful information. As far as I know, for one of the devices probe test, we're putting the reference files in one kernel CI repository. That might be a starter. But yeah, we just need to figure out which repository is more suitable and use it. About the variance between the subsequent runs, I was wondering if it should be just one value for every event that is being tracked, or if we need more granularity. Like, is this a per event value, or it's one value for all? And finally, one last doubt I have is about tracking the start or the end of the functions, or like tracking the duration of the functions. If you track the start and end times, as I did in the proof of concept, there's the drawback that if you get a failure very early in the boot, then you get a cascade of failures as a consequence. If you decide on using duration, then you have a lot of trace points. So I'm not sure which is the best way forward. So yeah, I'll open the floor for discussion. Please help me implement this test.
Hey there. Yes, I was just going to suggest, you brought up kernel CI earlier, and that's really good. I don't know if you attended yesterday at the referee track, the new kernel CI, you were there?
Yeah, no, I'm part of the team. That's
oh,
okay.
Excellent, cool, yeah. No, it seems very promising, especially in terms of just reporting. And the nice thing about it is that different vendors can have their different labs and stuff like that. So you can have kind of a distributed test environment, but a common reporting place. What I was just going to suggest, since you mentioned the effectively regression tests for performance regression tests for boot times, it's a really good idea to track, in my opinion, the start and end time, because often you'll have counters, and you can derive the duration easily from that. Although, as you point out, you can have a cascade of failures depending on the way your test is structured. But I would say that counters are really good because in a lot of cases they're much easier to deal with in reporting systems. And then it's a lot easier to deal with that in terms of if you want to do like a box graph where you've got, like your minimum, maximum, and like, first quartile or whatever, an average, right? But I think it's a good idea. And then just another question, I think it might be in one of the subsequent presentations, but also the bootloader timing is also important to consider. Pre-kernel boots.
Yeah. I don't know about that. Like, I'm just being limited to the kernel boot.
So I'll make a comment on the variance. I found in my own testing, I've been doing some boot time testing, and I found that it does need to be per event because you get there are some. Well, I have an init call test, right, and some of the init calls vary and some don't. And so it wouldn't be appropriate to apply like a large variance to the ones that don't. I mean, if they vary by even 10 microseconds, you probably want to know about it. So that's my feedback on that one.
Further question: if you're tracking all the init calls, are you going to have like criteria for each and every init call?
So I have a single criteria rule, but I have a reference value for every init call. So, and I had the idea this morning that I'm going to put if init calls can change a lot based on your kernel config, and so I also want to know if I was missing init calls or if there were extra init calls that tells me to hopefully update my reference value file. Oh,
yeah. Hi, so I've been working on boot time optimizations for Android of late. So we use Perfito tracing for Android. And some of these could be done through Perfito, certainly. For instance, start and end time tracking for each kernel worker threads or K threads. And you can see if there is any sequential dependency between kernel worker threads or what is actually hogging the CPUs. So it's worth, I haven't explored Perfito for Linux per se, because we have been using only on Android, but it should technically work some of these, whatever you have mentioned there.
You're referring to Perf, right?
Perfito.
Oh, Perfito. Okay, sorry.
Okay. Hi. So, yeah. We can also use that what's it, the histograms for int calls, so that we can what's it, make a histogram for each, or sorting that each init calls, which one is what's it, takes more time or something like that. In actually that in the only the kernel. With actually that with using that Perfito, we will what's it, make a more precise what's it, analysis with using that SQL or something like that. Yeah. The basic concept, I think that using that only what's it, simple tools like only the kernel or something like that. And if you have some resource, you can introduce that Perfito or something like that. Yeah.
I guess I have a question about Perfito. Have people used Perfito for early boot, like before the init is up, or? Okay. Okay. Oh, I should have let. Can you say that again?
I think it is doable, but it will require a little bit of a changes in the Perfito itself to stick to those whatever ftrace events which is required. But it is certainly doable, I think. Yeah.
Yeah, for the Perfito, I think that the Perfito doesn't support that dynamic, like a K-probes event or something like that, so that after stress events only currently, yeah.
So one question I had, which I think I asked Masami earlier in the week, is so one of the problems I have is I have clocks that don't come up until you're a ways into init. So does the trace clock, apparently there's different clocks, you can set trace clock to something else. Does ARM64 have like a instruction-based clock that I can access before the sketch clock comes up? Or if someone, I'll ask that on Linux Embedded or something, but that would help out a lot. So. Okay. We have a little bit more time for any additional questions. Let me see here. Oh, I wanted to say I thought the using boot config for the ftrace probe declarations, I thought that was pretty neat.
Yeah. Can you talk a bit more about how you establish the reference values file? That sounds like a hard step to take, and that makes it like hard to get started using what you produce.
So it's just a very basic Python script. You're meant to boot your kernel just once with the ftrace configuration that is provided and run this Python script, and it will just read the trace file, which is going to produce timings for the events that we're interested in. It will just dump them in a YAML file. So it just produces a YAML file, very simple, just the name of the function and the timestamps associated. and you can feed that into the test. So it's not supposed to be really fancy. It's just supposed to produce some kind of reference.
I'm wondering if you wouldn't get value out of keeping files for multiple commit IDs or tags versions. That way you can see evolutions and maybe understand more what's going on with your comparison. Because right now you compare it to some random run that you did that sounded okay to you, and that then you decided to keep as a reference.
Yeah, so first of all, I think the file itself, as it is proposed right now, is lacking a few data, like which kernel version, how did you test this, how did you build the kernel, etc. So more metadata should come and should be added. For like tracking the values over time, I think that's maybe more the job of a CI. Like, I'm not sure if there's a way to track all those config files.
So yeah, so if you generate your own reference value file, then your future tests are only going to be good to measure against, to find regressions, from that point on. If we can figure out a place to store things, then you can share that knowledge of what is a known good value with other developers. But we talked about this in the testing session. It has to be, there's so many variables that go into that, like CPU speed, number of cores, and other things that it really needs to have a lot of metadata associated with it so you can find the right known good value file, right? So in embedded, we're a little bit luckier because we have our hardware is more fixed, right? And so that helps with the combinatorial explosion of reference value files, but it's an issue. But once we have a place, then yeah, it would be great for someone to be able to, I just got a board, I download a known good reference file, and I know immediately if I've got some error on that board.
You might think that vendors and build systems are the right place to do it because, well, vendors want to support their boards and build systems have more control over the current state of things. So maybe that's one step to look into. I mean, kernel is nice to test because it's rather long to boot, but that doesn't cover enough and might not be, it doesn't cover the whole state. So things could change even though you didn't change anything in your kernel. And then what you just said is right.
I think it'd be great if the board vendors produced, reference value files so that people could test out of the box. So, but there's a whole infrastructure we got to set up to support that. So, yeah.
You don't want to store somewhere metadata, but just store boot logs. If you can run your script on boot logs and get whatever you want out of it, then you just host like paste files of a boot. Maybe you need to add some ftrace data, but that way it's much more simpler and you can extract new data out of it. If you change your script, then you can rerun it on the previous values. So, and that's simpler for vendors as well.
So this is all focused on the kernel profiling and kernel logging, but as we just saw in the first talk, the kernel is coming up fairly late in some of these things. So I'm wondering, this stuff is great for the kernel, but how do we get to a point also where maybe it's more of a CI lab thing, but we also want to know from the time you turn on power, when does the bootloader start? From the time the bootloader runs, when does it actually hand off to the kernel? And only then we can start doing kernel stuff, but we kind of need to be nice to have in all the CI systems some standard ways from power on to bootloader to kernel and have at least kind of those crude timestamps would go a long ways too, right?
Oh, over there. Okay. That's dangerous. I'm gonna. Okay.
So at least for UEFIs, there is a loader time US variable, which the bootloader could populate. So at least you have a time base.
Yeah, each bootloader only knows from its start, right? So, and that's if it has clock going. So, anything else? Okay. Well, I did have one comment on the show failures only. I think at a minimum, it would be nice to have a flag for like if a human runs the tool to say. So. And okay.
So maybe a bit controversial. Would it be useful to have this information in debugfs by default? So not depend on boot config and ftrace, but have it built into the kernel itself to have specific points, write timestamps or durations to some file in debugfs?
If you wait about 5 minutes, then the next presenter will have some stuff.
Thank you.
Okay, we'll actually start in about 4 minutes just to keep to schedule, so talk amongst yourselves. Yeah. Okay, let's go ahead and get back started. Okay, let's go ahead and get started again. I'm very excited. Like other presenters, I have more questions than answers here, but I do have some things I'm thinking about and working on. And as we go through the presentation, it gets more and more nebulous, just ideas rather than actual implementations. But so I want to talk about 3 separate things related to boot time, measuring and testing and stuff like that. So I always throw the abstract in just for future readers. So I'm going to talk about boot markers, boot phases, and automated optimizations. In the actual title that's in the schedule, I call it profile guided, but that's a very specific term. It's really, I learned earlier this week that it should be feedback directed optimization. So let's start with boot markers, and this actually plays right along with what Laura was already talking about, which is, well, just introduction. I don't think I need to go through this. To do regression testing, there's lots of instrumentation and tools that Laura talked about, but there's no actual test of boot time, right? So it's a little bit like there's a weight loss clinic and all they've got there is a mirror, right? So that's not that helpful to tell what exactly is wrong, where I need to fix things. So I think we need to pick a consistent set of time durations in the kernel to measure and report those, decide on what it is we want to report. So we already talked about the fact that init calls have too many. They vary a lot by different systems. They're not comprehensive. Print K messages depend a lot on config. If you're doing the serial console, you'll get a lot of extra overhead in outputting those. They're not fixed strings. But I do think that it's useful to talk about standardizing kind of the regions of boot that we want to measure. I think it would be useful just in order to collaborate, even if we're on different machines, to be able to talk about how much time did memory take to initialize, and how was it dependent on the size of memory on a particular system. So I'd like to come up with a tractable number of data points and with good kind of what I call cohesion of the data. So what things are kind of correlated to each other, and also what subsets can we blame for our problems and report regressions to. So there's a couple different proposed markers and methods. So Laura was doing trace events. I am actually proposing print case statements. But I think that there are other mechanisms, and I think we ought to have a system that works no matter which output mechanism you choose. So I can imagine there's things like early serial port access, or on some boards you have GPIO that you can do really fast, and it's not going to cause overhead on the system. I'd also like to use the same style of markers for the bootloader phase, the kernel phase, and user space, right? So that you can get a more holistic view of what's going on. And it'd be nice if we could use the same markers with multiple measuring tools. So in order to reduce overhead, I'd like you to be able to reduce the marker size to a very short string. It'd be nice if the markers were human readable and automation friendly. So this is what I came up with: boot markers, which is have 3 parts: a prefix, a number, and a string. Boot marker is one of B for bootloader, K for kernel, U for user space, numbers 1 through 9, and we can talk about whether that's too restrictive to just have 9 regions, and then a string indicating the region name. So the rationale for this is that if we're trying to restrict the overhead of measuring that on like print K when you're going over serial console, then you can reduce that to just the 2-digit number, the prefix and number, and it's only 2 characters going to the serial port. Well, 3 if you count the line feed. But and so I actually did some testing where I added boot marker. So I made a new routine in the kernel called boot marker that takes those, and I put it in a init.main, and I called it from some places. And this is the problem. I picked some arbitrarily, and I gave them names. I don't know if they're the right ones. So this is the output from a boot marker from print K with the demessage output with the boot markers enabled. I put them at critical level, log level, and you can see the timing duration. This is the start time for each of those, right? So, and I did, okay, so the one thing I kind of cheated on was I made K8 not a single region. I made it for each of the init call levels. So K8 has, I don't know, 8 levels or something like that. And so there's a couple of flaws you can see already just by looking at this, is that the sketch clock doesn't come on until you're a little ways in. So that's a problem. Hence my question in the earlier presentation. But what I have done to deal with a lot of these issues, so there's a tool that someone reminded me about just in the break. I use a tool called Grab Serial to grab the data from the serial port as things are coming up. And so as long as I'm getting serial output, I can do this measurement across the bootloader and across the kernel and across the user space, as long as the messages are coming out in a timely manner. And there is an issue with, during the early kernel startup, the kernel messages get buffered until the console is initialized. So that's an issue that you kind of have to compensate for. But I've recently most people don't know that there's this tool that's already in the kernel called show delta. It's in the kernel scripts directory, and it is used to show the delta between 2 times, or it can be used to show the delta between 2 times in a print K times formatted demessage output. So I made some slight modifications to it, so that you could pass it a string, and now it can measure a bunch of regions in the kernel. And in my case, I'm putting my string marker as boot marker, and now I've got durations for those regions. So it's between each boot marker output statement, I get a region, and then I've got, you have to have seen my earlier presentation today, but this is in KTOP format. These are the metrics for the duration, and then I can convert these unknown test case outputs into pass or fail based on a reference value file that I've got. Okay, so that's boot markers. That was real quick. Any comments on that? I've only got about 10 minutes per thing, so.
So there's a very old thing used in x86 debugging that is basically writing on the now abused port 80, which was used for the very early initialization of the system because it's available right from even in the boot block. So you can time everything.
Well, are you talking about the TMC instruction?
No. I'm talking about port 80.
Oh, port 80.
It's used to measure, it can be used to measure timing even when you have no memory.
Oh, okay. Okay, that's good to know. Okay. We'll go here.
You can avoid the buffering at the start using early print K, but that might not be available on your platform. I don't know.
Okay. Okay, early print K. That's good.
How useful is it to profile the init calls when you have like async probing and stuff? So there's not.
Yes.
Yeah, you might not have a one-to-one relation anyway.
Yes. One of the things I discovered, I don't know if you noticed that, but a lot of init calls do a deferred probe, or do a probe that gets deferred, and so you have this one init call, deferred probe init call or something like that has all this other stuff. So I would need to go in and account for that separately. I probably do something like that in my init call duration test because that's related to that specific kind of boot technology. Probably won't be able to account for it in boot markers. But that deferred probe comes out in one of the phases, and so you can kind of know that phase might be variable depending on.
I think that I would be most interested in the duration of each probe function. But
Okay.
that would mean you need a lot of identifiers.
Yeah, well, that's, yeah, so it's hard to know how granular to get. And that is a discussion that would be really good to have.
One of the things I've tried to use debugging heterogeneous systems is also ARM debuggers, debug subsystem sometimes has to, depending on the SoC, right? System trace macro cells, STM. So you could kind of write messages to it, and they are time-stamped, and you can read it later on. And
So is that an ARM-specific thing?
ARM64, yes,
Okay.
system trace macro cell.
Okay.
I don't know if there'll be others in other architecture as
Yeah,
well.
it's hard to find something that works across, any platform.
I was going to kind of echo the same thing. So that exists. I mean, you can use the M timer in RISC-V for that. It's cycle accurate. But one of the big concerns that I would have, especially if you get down to very specific things, like if you've got a PCI accelerator or something like that, where like even the variance between measurements could dwarf, or like your print K could dwarf the actual measurement.
Well, I found that if I don't put quiet on the command line, the print K times dwarfs the init call times.
So, and then in that case, the hardware-based debug, print, and or the bug trace things are actually pretty useful.
Yeah, they are, but they're machine specific and
so
platform
on your first
specific,
slide, you definitely said like we'll have to support multiple things. So even GPIO is like really good that way.
I really want to look into the trace clock issue to see if that helps out some. We only have like time for one more question because I got two more categories of stuff to talk about.
Okay, really quick. Why are we focusing on serial? I know bootloaders have serial. Is there a reason we can't do that part in serial, and then once you get into the kernel, not depend on serial? Is there a reason it has to be serial? Like, why limit ourselves? What's the like?
It's what I've got on my board, and it's universal. Like I said, I think it'd be useful to, but it's hard to find something that's universal, right?
Yeah, my point is, once you get into the kernel, it feels like this is overcomplicating it. Just use the normal logging or trace points to profile.
Well, okay, so, but the serial is working across the bootloader and user space, right? Which is not true is going to be true of any other
Correct.
tracing mechanism.
But maybe we can figure that part out, a common way to pass that information from the bootloader to the kernel.
Yeah,
so that it can kind of log those
things. There's been work
things.
on like sharing the tracing log between, the tracing buffer between U-boot and the kernel. But again, that's only one firmware, and so this is kind of a least common denominator approach that I found worked.
Yeah, my only worry is it becomes too low of a denominator, where the UART writing itself is going to mask anything. I don't know, that's my, but we don't need to stall on that.
I mean,
we can continue.
if you only got 3 characters per marker and 10 markers, you can figure out the overhead. It's not that bad. So anyway, I don't want to over.
I don't want to derail it, so I can continue.
Okay, I got to move on. So boot phases. This is what I want to do here is divide the boot into 2 main phases, the critical and the non-critical phase, and see if we can do a bunch of stuff in the critical phase to get those use cases that Kasim was talking about, get to those use cases up and running before we start a bunch of other junk, right? System D has like, I don't know, 400 services it wants to start up. And so the idea is to do only the essential initializations during the critical part of the boot phase. What this means is allowing deferred initializations. So the kernel already supports some mechanisms to defer initialization. The most obvious one is module loading, right? You can declare your driver as a module and then load it sometime later. There's no kind of easy mechanisms in existing RC systems or System D systems to identify individual drivers and where they should be in the thing. But it's possible to do things like that. So what kinds of things can be deferred? And I'm going to argue at least 2 things that I'm aware of. So deferred init calls and memory initialization. Maybe you didn't know that you could defer init calls. Well, there's this really obscure patch that I used at Sony like 10 to 15 years ago called the deferred init calls patch. I recently updated it to the 6.11 kernel, and I made it so it was really janky back then. So I have a patch that I'll send up if there's enough interest that puts the init call on a deferred list and then calls it later. Okay, I'll try to preempt what I assume to be the most obvious questions. Is this safe at all? I don't think so.
Okay. Actually, okay, here's the thing. My answer is actually it is. If you're using a device tree-based system, you can do 100% asynchronous probing. We do that on a Pixel 6, for example. We do parallelized module loading. So all of the things that you think are scary will actually work well because I implemented over a couple of years, implemented firmware doubling that basically makes your init call ordering completely irrelevant. You can put your consumer as the first init call and the supplier as the last init call. Everything will be stable. It'll work properly. So please give it a shot. Okay. There's actually a command line parameter. I gave a talk about it yesterday. There's a command line parameter to say, by default, do every probing to be asynchronous. Give that a shot. Okay. I think you'll see that cut the probing time by half in my use case.
Yeah, I talked to Bjorn. I don't know if Bjorn's here, but he said he had mixed experiences with async probing. So.
This will be a DT-based system, but if so, then I can help fix it.
I think that we can, that some of the init calls can be deferred by itself. So that this means that if we are, for example, the tracing most of the case, we don't trace that the boot time. So that in that case, the most of or all of the tracing initialization can be deferred.
Yeah, I found a couple that I tested just quickly that deferred no problem. My impression, okay, so if you look at the init call phases, the last one is called late init call, right? And my impression is that almost all the stuff in late init call is, I mean, it's intended to be loaded after a bunch of other stuff has been set up, the clocks, the power, the memory, the RAM buffers, the allocators. That stuff seems to be pretty safe, but you'd want to test it. So let me just say real quick. So I think part of this idea is to give people confidence that it's okay. We need to do some analysis and maybe say, look, here's the list of init calls that we think are pretty safe for you to defer. But like if you wander out in the weeds and try something that's in one of the early init calls, okay, you're on your own.
Yeah, so that I think that the command line this style will not be acceptable because it is very dangerous. Yeah, but each init call can declare that which one what kind of
that's an
the
idea.
condition it need to it can defer or it need to be this timing or something like that.
Okay, jot that down. So if the init call itself kind of declared that it was safe for deferral.
Actually, honestly, I would say if most of your init call delay is coming from device drivers, don't even bother trying to deal with reordering init calls. All you should be doing there is registering your drivers. Little one function call shouldn't take any time, and defer everything. Do asynchronous probing. All of that already works. Don't even reinvent the wheel. Just do driver async probe equal to star. That'll defer every probing.
Well, but you're still gonna. I mean, if you have a critical code path, if it's listed as an init call, it's gonna call it, right? So it's
but if the init call is just registering the driver, you don't do the actual probing. You do the probing separately.
Well, but you'd have to have a mechanism to tell the driver, right, that I don't want you to run as soon as you can. I want you to run.
I'm saying there's a command. I'm saying there's a command line for that.
Oh, is there? Okay.
It's exactly.
Okay.
Yeah.
That's good to know. I got to talk to you offline.
Yes, please.
Okay.
You're reinventing a lot of stuff. It's all done.
There's a couple of issues with this. This is just one of the techniques. Like there's some issues with when do you free init memory. Some init calls may be dependent on others. That goes into the safety issue. I think a lot of those in the late stage or the driver stage could probably be deferred, but we need testing. Deferred memory initializations. There was a good talk, really good talk at Open Source Summit in North America about deferring the memory initialization, so bringing up just the first like 1 gig or 2 gig of memory and then deferring the execution of the remaining memory until later. So that's another thing that could be deferred. And then I think I'd like to look at, I haven't looked at yet, but how you could go about, if you're going to have these different boot phases, how you can identify something as being in the critical phase versus the non-critical phase. So that's probably some system unit ordering and modification of the dependency graph there. That's about all I got on that. So are any last comments on that before I move on to my final thing?
Try to do parallelized module loading, please.
What? Sorry?
Try to load modules in parallel.
Okay.
That'll help. That helps a ton too.
Okay.
Somebody has here.
There is two things. First, init-ng used to be focused on doing that exactly. The second thing is, for some reason, kmod is the command line utility, not the library. I don't know exactly where the problem is. Fails to load in parallel. If you call it several times at once in parallel, some of the calls succeed and some fail. I didn't check why.
Is that mod probe or is it?
Yeah.
Okay. Okay.
I don't know why yet. I didn't debug it.
Okay. Unfortunately, I gotta keep moving because it looked like I only had one thing left, but I really have two. So I want to talk about the most controversial and least developed idea that I have, which is boot cache, statically compiled pre-initialization, and a boot time tuning tool. So what I want to do is automate the pre-initialization of the kernel. And so at a philosophical level, pre-initialization means I want to figure out what the hardware is going to look like before the kernel runs, and modify the kernel to be custom for that hardware. That means that there's a couple of ways to do that. So the problem with that, right, is if you specialize the kernel for a particular piece of hardware, you can't get the changes upstream, right? They're not general enough to share with other people. It goes completely against the whole notion of GKI and other initiatives, the device tree initiatives, to make it so that you can have a single kernel image that runs on multiple machines. But I still want to give it a go. I want to see if it's possible to automate that. There's no way it's tractable for an individual developer to go in and make all these specializations. And so what I'm proposing is something I'm calling a boot cache. So I want to record the values from one boot and then use them to reproduce the time in subsequent boots. Only it's not a runtime thing, it's a compile time thing. I want to record the values and then actually substitute in, let's see, this is the thing. So during the record phase, I want to add a kernel command line that says you're in this mode where you're recording data. And then I want to actually extract that recorded data, turn it into hard-coded macros that then the drivers can use to compile out the portions that they're not going to use. Okay, so I want to actually do it at the compiler level. So I think there's a question over here.
I'm actually kind of happy that you mentioned that, because from the Zephyr side, which is where I'm coming from these days, we actually do something really similar to that. So we have in device tree, you can get a dependency graph quite easily there. If things are disabled, then you just don't boot them automatically. You don't load them automatically, the drivers. But then we also have per bus, effectively, like an initialization priority. So you've got clocks with the highest priority, and then you'll have something like memory controllers, and then you'll have you'll eventually get to your I2C buses, and then your peripherals on those buses. Those NIP priorities are actually in kconfig, and they can be modified on a per board level because occasionally there are outliers. But what's great about this is you get a completely predetermined, what's the word I'm looking for? It's always going to be the same, deterministic.
Yeah,
it's always deterministic. It's like a guarantee. You can actually, at runtime, you can verify that it has booted deterministically, by flagging that option as enabled. So it's been working for us really well for like at least a year now.
Yeah, so the idea for this actually came from the Zephyr thing. So, and I don't know if it can translate into the kernel or not, because I'm talking about like taking, get OF platform or get property, and if I can replace that get property with it's a 4, use a 4. Yeah, it's compile time constant, so it should actually optimize the code as well. I don't know if it's possible though, because device trees deals with a lot with pointers, and you have to make sure the pointers are deterministic if you're going to do this type of thing. Okay, there's a question here and then over there.
Are you sure you're not reinventing hibernation?
Well, no, I'm not sure at all.
Because you do a boot, you hibernate, you keep that image as like the golden hibernation image, and you always de-hibernate from that image, and it's
the difference is that I didn't get a compiler pass over hibernation.
I would like to.
Oh, there was a question. Well, go ahead.
I would like to challenge whether this idea is really going to gain you so much, because iterating over device tree is not what you spend most of the time on, I think. I mean, what in my experience, what you spend time on is probing like USB devices or initializing, loading firmware to some huge chip.
Yeah, okay, so I want to make sure I explain that this is not just to eliminate device tree overhead. So device tree overhead on my board is about 130 milliseconds. And that could probably be reduced. Some of that is probably print case stuff. But it also applies to bus probing, right? So a lot of bus probing, especially USB bus, you have these standards mandated delays as you're getting what are the list of devices on the bus. And it's like, well, I know what the buses are the devices are on the bus.
You have to do that, otherwise the device doesn't initialize. So how?
Well, right. So you have to separate the initialization from There are issues. There's a lot of huge issues here. Wait. So this guy's been waiting for the thing. Go.
Okay, so maybe just for the record, with U-boot you have the Falcon boot, which is something as you described for running the kernel with stored values. So you don't need to you store one value of the boot and then use that stored value to boot the kernel faster. Second approach is that in U-boot you already have the platform data optimizer, which is taking the device tree for the U-boot. There is a special Python tool. It extracts it, changes it to the C structure values, and then you just use that precompiled code for your faster boot. This is used for very tiny boards, which needs to be like 32 kilobytes for the free-stage bootloader. So there is such thing is already implemented in U-boot. If you would like to look for like something similar.
Yeah, I would love to look at that. What was it called again?
This is called the platform data, plat data.
I can leave you. And there's an optimizer inside U-boot or something?
There is a tool in Python which is taking the device tree. It's looking on the device tree, extracts what you need, changes it for the structure in C, and then you use that C structures when you compile the code. And then you have the portions of the device which are important for your fast boot, and tiny device, you just use it automatically.
Okay. Last one, Masami, and then I have one more thing.
Oh. Yeah, just what's it? Why you need to wait for the probing, the bus probing, like a USB bus probing? Because it's I think I thought that is a user space issue.
Well, I'm trying to get the CAN bus up in under 100 milliseconds, and so
yeah,
I don't want to probe for 50 milliseconds.
Yeah, but
even if it's asynchronous, I mean.
No, we don't. We can defer that after booting up the user space, and the user space will just probe that.
Well, I mean, if the CAN driver is going to be initialized in the kernel, right, then.
Oh, yeah.
Likely there's all kinds of gotchas that make this impossible, but I thought I'd throw it out there.
Yeah, so I mean, you can follow the idea of GKI. You don't have to use a GKI kernel, but make your kernel fully modular. Load only the modules you care about for the most immediate needs, and then load the rest later on.
Well, yes. I mean, there's always modules, but again, I know for a fact that some of the init calls have these timeouts in them while they're waiting for stuff to come back.
If they're all driver-related timeouts, then like, then if you make it a
I think
module,
those should be investigated to see if they could be reduced or removed.
yeah, right.
for the
Just
caching area.
FYI, every Android phone in the past 3 years or 4 years, they're fully modular kernels, and almost all of them use parallelized module loading.
Okay,
so it's all solved.
So you're saying that Android solves this by putting as much stuff in modules as possible?
This is not the intent, but I'm saying the features you're looking for are already there because we did it for other reasons.
Okay.
But it's there, yeah.
Okay, last thing I want to talk about with my 0 time remaining, but we're on a break. You got to give me. I want to be able to give developers a tool to automatically tell them what they've done wrong or what they could improve. And this would just be something that looks at their kernel command line, looks at the loaded modules, and tells them, oh, hey, you know, if determine if you're using if you have clock disable unused in your init calls and it's taking more than 0 microseconds, there's actually a kernel command line option that will disable that. So you can trade off a little memory for, or I don't know if it's runtime performance, but I think there's a lot of stuff like that. I think some were mentioned here, that there are existing techniques to reduce the overhead of some of these initialization things that are available that we could point people to.
That particular command line will cause permanent power impact for the rest of your boot.
What?
So that particular clock ignore unused, don't do that. You're going to have high power for the rest of the time until you reboot
that's why. Well, no, see, I would make that a candidate. I'd make that a candidate for deferred init calls. So that's, anyway. Okay, I have more stuff. I wanted to talk the same thing as Kasim did, which is there's no boot time maintainer in the kernel. We don't have an ecosystem really of boot times, developers, and how we can collaborate. We already had the discussion though, and we're out of time, so thanks. And you can talk to me in the hallway.
Powering off all those I2C regulators takes a lot of time too, so don't do it.
drink water. When are we coming back? At 5?
können wir uns mal über. Stimmt, du hast ja auch noch das Problem dabei, ja. So, I think we are ready to start again. So yeah, as I said before, we have broken that up in different topic areas basically. So the next two sessions will be mostly on towards connectivity. The first one from me talking about Linux WPAN. Just a reference for everyone who's not really familiar with that. So basically that's IEEE 802.15.4, which is a spec for low power wireless basically. It's used in things like Zigbee and Thread and so on. So that's mostly more on the embedded side for microcontrollers and so on. But we have a Linux subsystem for quite a while on that one. And we want to do some regular updates here to see what's going on. And I actually want to use it as a discussion place as well. So a colleague maintainer of mine, Alexander, is online as well. So if you want, Alex, if you want to raise your voice or something, make sure that you're coming in with microphone and camera and so on, right? And yeah, so let's get started here.
Yeah, thank you.
So the agenda, we have different file layers basically that we are supporting. The one we're heavily supporting is 2.4 gigahertz. There's not really much to update on that front. But there's also things like sub-gigahertz and ultra-wideband that are in newer standards of the specification. There are some different use cases for that could be interesting, so I want to touch upon that. Then there's in general the management layer support stuff we have been doing. So Miguel, who comes in here, has worked on that quite a bit. I want to talk a little bit about like what we have there, what are the gaps, what is missing. And then one thing that comes up now and again is that there are companies or vendors or just people that want to use their own stack on top of what we're having, just reusing some of the PHY and the basic low-level driver basically, and want to use the rest of that in user space and so on. So it's a bit of a difficult situation for us how we want to deal with that from a kernel perspective. And then I am also looking for a little bit of feedback for a user space component we need to write basically as a PAN coordinator to handle all the devices and so on. So that's basically the topics I'm touching. Feel free to interrupt me anytime here. This is supposed to be a session on discussion and so on. That I only have like 5 or 6 slides anyway, so feel free to go into that. Okay, so sub-gigahertz. There is partial support for file layer on that. We also have one driver that actually supports it. That does exist. We don't have anything in 15.4 I'm aware of that we are lacking there to support that. But maybe on the more extended feature set or something like that on some use cases, that might be the case. So if anyone here has a use case for that, please let me know. If not, we can go over that. So I know that the people from BeagleBoard and so on are interested in that. They have a device called Beagle Connect, and that is running on sub-gigahertz as well. But there's support on Zephyr on that side, so we could actually have like testing going back and forth. But besides that, there's no one really stepping up on doing any work on that so far. I mean, I know that the people from BeagleBoard wanted to do that, but I mean, they're lacking resources as everybody else, so that's not going to happen right now. So if you don't have any comments or questions on that, we can skip forward to the next one. Okay. The mic?
It's there.
Yeah, actually, for the CC13XX platform, they just added sub-gigahertz support in Zephyr. I'm pretty sure if it hasn't been merged already, it's like in the process of being merged. But aside from, I mean, it's all actually working pretty well. Florian Grandl is maintainer now of 802.15.4 in Zephyr, and he's actually doing a really great job keeping to the specs. So.
Yeah, I mean. Oh, Alex, yeah, feel free, go ahead.
Yeah, I think what the most people are concerned about the sub-gigahertz area is that there's a lot of regulations. And it is always different in the different countries. And we was talking about one to add some 802.15.4 to the regular regulator database of wireless, but I think a lot of people concerned about this, that they cannot at least verify that the specific file has a specific setting that's not allowed to use in some different countries.
Yeah, I mean, you touched on that. So we had the idea of using like the DirectDB stuff that wireless people are using or something. We could extend that or have our own version of that or something. So that is possible, but it really depends on actual companies or people using it. So before we go that route and do all the work for that.
Oh, no, I was just getting the mic.
Okay.
Last time I looked into it, there might not have been complete sub-gigahertz support in Linux, but I haven't checked in a while.
I mean, as I said, there might be gaps. So I know that we have like at least more of the file layers listed. I have one USB device that is actually using a sub-gigahertz transceiver on it. So that's a variant of the 80 USB with different firmware and so on. So that is there, but I have nothing really to test it against. To be fair, I have a Beagle Connect at home, so I need to find the time to actually do that. But yeah. In general, I'm looking more for like people that actually want to use that and have use cases before we do more work in that regard. Okay, so basically with that, similar to that, we have ultra-wideband. That is newer, and a lot of people have more interest in that because of like the possibilities that it opens up in terms of like speed of connection, or also services like location arranging or stuff like that. So there is no real good support for that. We don't have any hardware support for it right now. There need to be added additions to the file layer support and so on. I don't think for Mac we need anything. Miguel, please correct me if I'm wrong there. So Mac should be okay. So that's all the same. And then on top of that, you could go ahead and have services like location ranging and so on. So that is what people could really be interested in. But for that, we would need to get all the plumbing basically in place. So again, this would be how much interest is there. So is there other people around that actually want to do that, have that in products, have them maybe something out of tree that they want to use or so. I need to really understand like where to allocate our resources in a really tiny project here, how to do that. Anyone? So then I have a question for Miguel. So, I mean, we talked about that before offline. So I know that you have been working on some ultra-wideband drivers. So maybe you can give us like a summary of what the status is. Is that something we can expect to get in? Is that, how difficult it would be?
Yeah. So indeed, I worked a bit on the ultra-wideband support recently. It didn't make it upstream because so far, indeed, there is no working hardware with the mainline Linux and all the changes I managed to do. There are many small things that needed to be improved in the core in order to be able to support those devices. And I believe in the core, I have something that is now pretty okay, even though it needs a little bit more polishing. But otherwise, it should handle all the specificities of those devices. But with the lack of working hardware right now, it's still in my Git tree. However, of course, if anyone wants to play a little bit with it, I planned on sending it once the hardware was working. So far, I didn't manage to reach that point, but that's of course something that can be shared.
Can you not just
Alex,
go ahead.
I was just going to ask if there are any chipsets that are particularly good for ultra-wideband, even if it's not mass-produced or something. If someone else wants to evaluate it and see how it goes, can you recommend anything?
So, I mean, I think it's said, but there was Decawave that was before, and they bought Bakovo. Hopefully I pronounced that correctly. And I think that could be something that is available off the shelf. I mean, that's one of the things I talked to Miguel before. I'm a bit reluctant to get all the stuff in if there's no hardware easily available to get and off the shelf and buy and play around with. But if that is the case and we have at least a basic driver for that, I would be happy to expand the support we have for ultra-wideband. So that would be
Indeed, the DW3000 is the device I tried to make up and working. So far it was a failure, but there is a bit of code trying to make it work. The kind of issue with it is that it's very complex, and the design of this chip involves a lot of register configuration for the RF part. So even without going too deep into the configuration, I mean, without using any advanced features like the ranging thing and so on, just sending a data packet is, it involves a lot of configuration. But it is definitely feasible, and Qorvo shares support for it. There is a public repository with a lot of configuration, but still it works. I tested it.
Okay. So I mean, I would hope that when you find the time to actually work on that a bit more and then send out an RFC, I would really appreciate that, and then we can look from there. I would also really be interested in what kind of changes we need to. I mean, there will be some smaller file changes, but I think that might be easy to do. But for the Mac layer, for all the extra services you run on top, I mean, that also comes in with newer specs that we are not supporting. I mean, basically, we are supporting an IEEE spec that is coming from 2006. And there are many, many newer versions by now. I think the latest one is from 2020. And so really catching up on all these things. But I only want to do that if we have actual some use cases drives that actually make use of that. Because without that, it's just that code that we have lying around and nobody's using or maintaining it. So.
Slightly, maybe something that is slightly complex to implement in Linux is the timing requirements. For the location and ranging part, we need to be very precise and know exactly when the packet goes out and goes in. So we might need some extra channels to handle that, and I have no idea exactly how it should be implemented in the Mac part. But we will need at some point a straightforward way to stamp the packets, or at least tell the packet scheduler when it needs to send the packets, and synchronize that with the Linux clocks.
Okay. Does the hardware actually have some timer support that we can, some hardware timer that we can use for that also? I mean, because some of the chips I've seen are very, very simple and don't have anything of that. But some of the more advanced chips or something, they have like additional timers for that and so.
Yeah, I think there is some hardware for that, but currently no part of the framework is capable of handling that. And what needs to be done is synchronizing with your own clocks.
How are the chips connected? Via SPI?
Yeah, most of them, I would say like 80-90% of them are really just SPI and then
you
additional 3 or 4 GPIOs for reset.
In your SPI message, you can add a timestamp pointer, and then the SPI framework takes a timestamp.
Oh, and then we can get it from there, and then that's good.
A system timestamp.
Okay, thank you. That's good.
And if you really need precise timestamps, you can hack your SPI driver to do not DMA but polling and stuff, and even stop interrupts. But
okay,
Vladimir,
now I'm looking at more like from a maintainer platform perspective. So, but for a product that would definitely might help. But
Vladimir Oltan has done it for the SPI switches, the Ethernet switches which are connected via SPI for PTP stuff.
Nope. I just saw actually on the Zephyr Discord, Johan F. Mentioned that we actually do have DW1000 support in the Zephyr tree today. So if anybody's ready to play around with it, and I think it's on, yeah, and I think it's on, there's an NRF MCU attached to that, so should be 100% supported. So if anybody wants to play around with that, that's a great platform, it sounds like. Yeah, yeah. Upgrade, I guess.
Any more comments, questions on that? Alex, anything from you, Noah?
No, but if there's some Mac, soft Mac requirements, and Sapphire already supports it, I think we don't need any hardware for this. We can find a way to connect it over HW simulator. I already did that with AF packet and WoW packets that I have simply the user space stack, and if Sapphire has a platform to run as a F binary in some kind of sandbox mode, I think this is possible to have some testing. Yeah, to play around with it.
It's more the question if like some of the timing requirements that come from the spec from something like ultra wideband or vSUN or something like that, they have specific hard timing requirements that are sometimes difficult to handle with Linux. But I mean, we have preempt RT now, so you can fall back to that. Okay.
Maybe you can look at what the Wi-Fi pipe people are doing for the Wi-Fi ranging stuff. There are basically timers in the hardware which can timestamp your packets, and you can synchronize these timers with a system clock, and then you don't need real-time reactions to packets, but you only need precise timestamping in the Mac or Phi.
That was the reason why I was asking for the timers of the chipset, because I was counting.
That's also possible for time-triggered CAN and so on. So these mechanisms are pretty common.
Okay, so if you're good with that, I would move to the next topic. We only have like 8 minutes left. So MLE support. I mean, that's something what Miguel was working on. For a long time, we didn't have anything like that. Now we have a good set. We have like beacon sending, we have beacon scanning for beacons active and passive. We have association, disassociation of devices and so on. There are more things, as I mentioned before, we see newer spec versions coming in. There are more things available that we could or should implement. Just this week, someone mentioned on the mailing list the PHR for extended MTU. So normally 15.04 has only like 127 octets of MTU. It's really small, but for machine to machine, that's normally okay. But now they have mechanisms in place to actually extend that to 2,480, 2,084, 48. Come on. And that's something we might want to implement, but that is really opening up a lot of can of worms in our stack currently, because we kind of expect this kind of size. So we need to see how easy it is to do that, and so on. Then we have some more additional bands and support in the FIs. I think a lot of that was already added, but there might be more coming in. But a lot of these things are, more or less like easy defines in some tables and so on. You can get added, and then it really depends on the hardware support to actually use that and make sure that we synchronize that with the stack correctly and so on. Anything on that? Do you have any? So all of the stuff you had on that is merged already, right? Yeah. So okay, nothing pending also. So good. Okay. But with that, let me go to the other one first. So based on the MLE stuff, we now have that all in the kernel. We have some small tools in user space to actually test that, trigger and scan and so on to make sure everything's working, or sending out beacons and so on. That is working fine. But we need actually a service now that is running and making sure that it handles the network correctly. So in 15.4 terms, that's a PAN, Personal Area Network Coordinator, that is handling stuff like sending out the beacons, getting the requests for association, handing out a short address, and so on, keeping the leaves, basically like the DHCP server and so on, doing all of kinds of these things. So that would be something we need to get started at some point. I just want to make sure that nobody else is already working on that. So I don't know, Miguel, Alex, anyone of you having code for that, or?
So I don't have any coordinator, user space service, proof of concept like that. However, I shared with all the commits I've sent on the mailing list, in particular in the cover letters, all the exchanges that were needed from user space. So it is very easy to replicate and have a very small setup with the discovery, all the commands with the discovery, the association, and so on. So now there is just the coding part, that needs to be done if we want to create this service. Plus adding all the logic, especially when you want to create a group of devices for allowing or disallowing new devices to join your PAN. So this is something that has not been handled so far.
No, I'm aware of that. I tested all of these things before with the tooling we have. I just wanted to understand if there's something already that we can get started, or if that's something we basically start from scratch. So yeah, there would be other things that could be added to this service, which are not necessary for the basic stuff, but it could be something like making sure that we have the API values available for routing protocols that are interested in that. And also things like generic header compression, they have like specific mechanisms actually to let other nodes know that they support these compression techniques. And we could send out the neighbor discovery messages in then and collecting it from the other nodes to make sure that these are shared correctly and so on. So that could be something to be added into that one as well. I will think about that a little bit more, and then we can talk about that on the main list and figure out how to start on that one basically. So. Is there a question? So let me go back to the other one. So I mentioned that initially there are stacks that are running various things, like there's ZBoss for Zigbee, there's OpenThread, which does the thread protocol implementation, there's some BSON stack and so on. So there are all of them, basically they run in user space and want to find a way to use the hardware directly from us. So all of them can use things like SPI dev or so, fall back to that, and then do all the implementation in user space directly. There's been various discussions with these projects if we can find a way to use our file layer and Mac support and so on. It always falls short at some point because we didn't support something they needed, or they have like some optimized routines and so on, or they just want to have like a better control over their source code and so on. So right now, I always said like I'm not interested in supporting them in a way that they can use their own stack and not working together with us. But I feel a bit more guilty about that recently because we are not catching up. We are not providing all the stuff they need. So I wanted to reach out here and see from other people what kind of experience they had with opening up low-level driver access in their subsystem or something like that. because right now that feels like a terrible choice to do. But sometimes I'm wondering if that is still an option if we find like some good middle ground there. So I'm not sure if anybody has real experience with that here or so, but I wanted at least to bring that up here because that is a crowd that can comment on that. Don't be shy. It doesn't have to be like a full answer. Oh. Fair enough.
Yeah.
Alex, go ahead.
Yeah, I think for that we need to provide a better socket interface because it always depends what they're doing on the Mac layer, and there are some special frame types which we don't support because the only socket interface only can transmit some data frames, so far I know. And yeah, we just don't provide anything what they can do otherwise. No.
Yeah, no, I agree. I mean, it's definitely it's not something we can just say, okay, just start using it or something and it'll be good. It would also something we need to support, and I don't know if that is worthwhile to spend any energy on that one instead of like fixing up the stuff that they need to do. I mean, that was just an idea I want to throw out there because it feels like a few years we are dragging around that and there's no progress on that. But on the other hand, with the work Miguel was doing on the MLE stuff and so on, there's a lot of gaps closed already, so maybe that is helping.
Yes, I agree that this goes into the right direction to support that.
Okay, so with that, I'm running out of time. So thank you all for listening in. Thanks for your comments, and then the next speaker's up.
Right now.
Right now, okay. Hello, I'm Mark. I'm maintainer of the Linux CAN subsystem, and Alexei is with me. He is doing the J1939 stuff. And to bring you all on the same page, what is CAN? Yeah, yesterday evening.
I copied them at like 1 a.m.
Maybe? No.
Let me look.
Okay. Maybe Alexei, you can.
Okay, here I'm taking over until the new version, which will be downloaded. I am Alexei Rempel. I'm maintaining the J1939 stack. It is CAN-based stack and used usually in heavy-duty vehicles, tractors or boats, marine, and so on. It was designed to combine, to allow different vendors to produce components which are compatible with each other. So people like, I don't know, you can, if you have a tractor, you can buy a terminal and some extra additional stuff, plug it, and it should just work. To allow this capability, there are different parts defined. First of all, there is a transport part, like somehow like TCP, so you can transfer more data, longer transfers, because usual constraints in CAN, you can max the payload is only 8 bytes, and to combine everything to something longer, you need need extra protocol, and J9039 is doing this. So you are able to transfer up to like 120 megabytes. Second part, which is addressed by this protocol, is address claiming. It is somehow similar to DHCP and kind of DNS combination. So different components are able to get or to announce own address on the bus without making conflict. So addresses are not just taken, they are communicating with each other and saying like, I'm taking address 8 and the other one, oh, I'm here on 8.2, and based on naming, there will be some kind of update like, oh, my name is cooler or better, so my address is staying on this place. Can't make it here anything. Here's the new version. Okay, I'm skipping Mark's part and going back to my. Yeah. And the protocol provides even high-level specifications, some think like file server is defined by isobus, which is high-level specification on top of J9039. For example, you can implement something like FTP server or HTTP server. So terminals are usually called virtual terminal. They will download some information from your extra components which attached on the bus, and you will get already some view of the system and some buttons and so on. As maintainer, I usually care about, well, maintaining, extending framework, making it stable, and fixing SUSE board reports and so on. But it's not matter how good the coder is. If there is no infrastructure, it's not really interesting. So I was knocking to different doors and asking to show me something if it's used. And here's one example. I was not allowed to show end product, which is using this kernel stack, but this is a step till the end product, which is green board, which is actually using kernel stack, and as you can see, it is showing functionality of the component like this one, and it is made by this virtual terminal, which is transferring all the data, showing the structure and so on. So this information is not part of the virtual terminal actually, but of the component provided by this. Sadly, this virtual terminal implementation is not open source. Yeah, and I have seen there are some fun projects. One of developers notified us on Ken utils. This is just some existing heavy-duty cluster, which is attached to the game Euro Truck Simulator 2, and it is using Linux kernel J39 stack, which is just working in this case. There are some other applications. Some of them was made earlier. Some of them I created just last year. As you can see, there is address claiming daemon. It is kind of DHCP variant for J9039. It can be used in production as well. Usually you just need to start it and say what addresses would you like to claim and what is the name of your application. Then there's J9039 cat. It is not really usable for end product, but it is good for testing. You can just take this application and get some data as input and send it over CAN and receive it with same application on the other side. So you can just transfer your files or whatever. It works. The SPI, well, it's just kind of monitor which is only showing you the frames. Then SR, simple send read application. And the Isobus FS, this is the application I made this year. It is kind of file server. And in this case, it is both server and client. So both parts are implemented, and if you like it, you can use it. I licensed it as LGPL, so you can link it in your application if you like, or work it like this. It is command line. It has command line interface on the client side and just simple server. And I implemented time date. It is according to the J9039 standard, which is again. No, this is only, this is both sides. You can run server on one side, which will get local system time on one side, and another side you can just ask what is the system time of this remote MCU which is attached on the bus. And currently I'm working on virtual position service. There are two types of standard. One is plain J9039, which is less precise, and there is NMEA 2000 for boards, which provide more information. Both of them should be supported by this application. And so far, I implemented the server part, which is working with GPS-D server. So you can, if you like, you can just take Raspberry Pi, attach GPS receiver, run GPS-D server, and start my application. And all of this should theoretically work compatible with any boat or any tractor. So you'll need on other side only some terminal which will show your position and use it as something. I'm still planning to do the client part as well, which should use this application again and inject the data to the GPS-D again.
Is that working well? Because I have had problems with latency with GPS-D.
Sorry?
So with GPS-D, I've had problems with the latency. So if you want, in vehicle, you typically want, depends on what it's used for, but if it's used for like, autonomous ish things, then the latency has to be low, and GPS-D tends to be problematic then.
Well, everything what is transferred over CAN is kind of with some latency.
Yeah, but the CAN bus has a guaranteed latency. Well, GPS-D tends to.
Currently, I didn't investigate this deeper. It was just like proof of concept, and if you like it, you can test it. Yeah, here's some example how it was working. The top part is the GPS-D client, which is showing current position. The second part is just a CAN dump, which is showing, okay, they are transferring the data over CAN with all related positions. And the last one is a client, which is receiving all of these positions. But currently, there was nothing using for some usable application. So I'm trying hard to get as much attention as possible for this stack because, well, the customer for who this stack was needed is using it, they're happy, and it works and so on. But I have no real time to extend it, and I'm trying to present it to other customers, but currently with no luck. So yeah. Everyone is welcome. I'm trying to provide as much tools as possible and get some testing against applications or validation applications which are available at least by the customer who is needing this stack. At least Isobus file server was validated, and the kernel stack was validated as well. And it was validated not only by these tools. I had some feedback from Huawei, which are, I don't know why, but they seem to have some interest and provided some feedback, like some things was not according to the specification and so on. Yeah.
I wanted to have at least 5 minutes. So going back to the beginning, you all have now heard about CAN. The basics, it's protocol from the 80s. It's just 8 bytes in the original version, 64 bytes in the what is currently deployed. There's no flow control, and this is together all a problem on most controllers. Usually the IP core receives a packet, generates IRQ, then the kernel runs the IRQ handler, and what you should do, at least what the network guys say, you mask the IRQ, and then you schedule NAPI, and NAPI, which runs in soft IRQ context or as a kernel thread, does the rest of the work. For CAN, because most controllers don't support DMA, you allocate your SKB, copy the data from the controller, and push everything into the networking stack. And in NAPI, you use the function netif receive SKB for this, and everything is fine. But we don't have DMA, and so the IP cores have to store the incoming packets in their internal buffers, and these are, if it's a good controller, 32 by 32 frames. But on a typical CAN bus, you can have a really high number of CAN frames, and this makes up to 10,000 IRQs or frames per second, and then you can do the calculation, you can do the math yourself, how many interrupts you have until your 32 frames of buffer is full. And then you, on small systems or loaded systems, or even on loaded small systems, the latency between the interrupt and when the NAPI runs is most of the times, if it's a really busy system, too high, and then you get packet loss. This is not good. And because there's no flow control, can most upper layer protocols rely on that the packets are received. And yeah, how to avoid this? Should we do as we did in the good old days before we had NAPI? Basically do the work in the IRQ handler, but you cannot use the function that is used in NAPI. You have to use netifrx. Ask the network guys why this is a different function, probably because of locking and whatever. The downside is this function works from IRQ, the other not, but the downside is this function is prone to mess up the order of the incoming packets. Because we have no flow control in CAN, this is an absolute nightmare for all protocols. So we have to do something in between. And this is where Eric's offload comes in. It's a helper. The interrupt handler comes, and then you copy your data from the IP core, push it into a queue either by timestamp or you just append it to the queue, and then you say Rx offload, yeah, I'm finished with my IRQ handler, or you need a different function if it's a threaded IRQ, and then you kick on the NAPI. And the NAPI iterates over this queue that we have in software and uses the correct function, the net IF receive SKB, so that the networking stack is happy and all the packets come into the stack in the right order. And the CAN guys are happy that they receive, even under heavy loads, all the CAN frames. Even on systems with many cores, we have seen this problem. So networking drivers, CAN networking drivers really should implement this and not do NAPI because the latency might be too high. And then I want to just mention timestamping. Timestamping is very nice to have in CAN, and you usually have a different free running timer in your IP core, and you somehow have to express this in the kernel representation, which is nanoseconds, and you have to do the calculation from the internal timer to the kernel stuff. And the clock guys have implemented these helpers. This is a cycle counter and time counter framework. You have to fill out this struct, a read function. You have to say how many bits of information are valid on your timestamp. And you say multiply the timestamp by this and shift it by that, then you get nanoseconds. Please implement this if you want to do timestamping. Don't invent everything on your own. It's already in the kernel. And this also takes care with another helper of calculating the internal timestamp to the kernel version, and the other way around if you need to. And you can set up a worker that takes care of overflows in your free running timer. This might be even interesting for your wideband stuff. If you have a free running timer in there, you can use this cycle counter, time counter to calculate, to convert it into nanoseconds. Yeah.
Got a question real quick?
Questions?
We probably only have time for one or two questions. Yeah.
Yeah. Do you need some kind of drift compensation? Because do you need some kind of drift compensation because the CAN clock is probably not going to have the same clock source as the kernel clock?
I had something. I attached the CAN internal clock to PTP so that you can run the functions to have a control loop to match one clock to the other so that they don't drift apart. But haven't used it in production. But you can have hardware timestamps, and yeah, they tend to drift because they are not perfectly synchronous, but you can. I have attached PTP stuff to it, so at least you can locally track both clocks if you want to.
Cut it off there. So.
Was one question?
So, any more questions? Otherwise, take it in the hallway maybe, and we need to move to the next. Sorry about the presentation mix-up.
Yeah. More time for Alexei with the. Midnight.
Yeah, I don't know when I copied them down. It was close to midnight.
Maybe there's a little bit delay or something, but in general it should be fine.
Okay, so hi everybody. So this is a discussion about hot pluggable hardware on non-discoverable buses using runtime loadable device tree overlays. I'm Luca, and my colleague Hervé is working with me on this project. So Hervé is going to introduce you the project.
See, so the context is for a healthcare product. We have already a quite advanced hardware prototype. In fact, it's going to be launched next year. So it's a classical ARM64 embedded system on one side and some add-on boards on the other side. So on the main board, we have the SoC and a bunch of resources connected to a connector, such as GPIO, some buses, such as I2C, DSI for some display, that all while on a connector, and we have several add-on boards that can be connected and disconnected by the end user of the product at some times when the system is running, anytime when the system is running, and we have some devices on this add-on board related to display, related to some sensors, and all that stuff. So we already supported device tree on the baseboard. We have adding some hardware, and to do that, we have thought about device tree overlays. So we wrote connector drivers, we load overlays, 2 overlays in 2 steps, because we need to identify the add-on board, and to do that, we have some IDs stored in EEPROM on the add-on board. So we have a first overlay describing this EEPROM, and based on the value we read on the EEPROM, we can select the second overlay and apply this overlay. So this works pretty well, I would say, but some issues are still open on this kind of topic. Just for information, we pointed out some related works from several people we know working on this kind of stuff, so feel free to have a look if you need some more information. There is some pointers.
I just wanted to mention also my own attempt to upstream Raspberry Pi RP1 support that is currently under discussion in mailing list, and is basically based on the same approach that you used on the microchip LAN 96X.
Okay.
Yeah, so
just a fast one. So we use that at the previous company, like same use case, out-pluggable board. And the issue we had is when we remove the board, we remove the overlay, but then we get a message that it will leak memory. So I don't know if this is fixed or.
Yeah, this is a point we faced.
Okay, thank you.
And actually, this opens something about device tree bindings. So let me just first introduce the bindings. Where is it? Yeah. So as you can see, there is a connector node. So it's a device. It has a compatible string. It has a driver. So it populates as a device. It uses the GPIO to know whether there is something connected. And then we have some nodes which are a bit unusual in some sense. So there is this I2C dash whatever for each I2C bus on the connector, going through the connector where the controller is on the baseboard. This node points to the actual controller, which is on the baseboard, but it's empty for now. Something somewhat similar for the DSI BDO bus. There is this kind of classic DSI representation with ports, and there is only one port, which is the one facing the main board, so the one from the CPU. And then when we added the overlay, one key thing was to use overlays in the way that appears to us as the appropriate use of overlays. So you add hardware and then you add overlays, representing this additional hardware. And new hardware is represented by new nodes. Each device is a new node. That's true for many cases. There are gray areas, but as you can see in the I2C debut node, which was in the base tree, we are adding in here one subnode, which is one device. It's an EEPROM, which contains the model ID. So in this case, there is no problem with properties. We are not adding properties. If the problem exists if you add properties in an overlay to a node that is already in the live tree. So you can add properties inside nodes, but not at the top level of the overlay. One goal for the V3 of the patch set was to remove all of them. We are adding devices, so we want to add nodes. we only have two left, which is the NVMe cells and NVMe cell names, which are used for now for the connector driver to access the NVMe cell and read the model ID. We are working on how to remove also those two. So the goal is to not use them at all. We discussed that with Christophe also yesterday, and that seems to be the correct way. This is something that was suggested by Rob, and it really seems to be the correct way to go. So I hope this kind of answered your question. So the next step, so with the first overlay, the driver is able to access the NVMe cell, know the model ID, and then it loads the appropriate second overlay with everything else on the add-on, on the specific model. So in this example, we have, again, the DSI port node, which contains the other port, the other side of the connector, leading to whatever is on the add-on, so the continuation of the video pipeline. And then there is the devices node, which is where we put, well, basically it's platform devices in the Linux kernel sense. So it's devices which have, in our case, no bus at all, like regulators and similar simple devices, which, which Linux will probe as platform devices. Yes,
I had a question. Typically, platform devices, you do memory mapped I/O. You can just access them directly. I thought this is sitting across a connector. How do you handle them as platform devices?
Well, platform devices are in two families. Basically, those on a memory mapped I/O bus and those without any bus. They are implemented as platform devices in Linux. The first category does not exist in our case, and I think it's pretty unlikely to exist in a real connector because it would have so many lines. It would be really a huge connector. People nowadays use USB, PCI, whatever. So I don't expect that to even exist.
So, like, how do you talk to the I2C controller sitting on the other bus?
Well, those are not actually on any bus. So they are added as if they were at the top level of the device tree, but in the practice, they don't connect to any bus.
Just to help, the I2C controller is in the SoC, and the I2C bus goes through the connector. Right? So if you're talking to I2C, when you talk to the platform devices, it's regulators. You don't talk to them. It's a fixed regulator. It's just a power rail on your add-on board. So there's no communication with it. It's just on.
So yeah, back to the bindings. So the only remaining problem about bindings is NVMe cells and NVMe cell names, as I told. So we are considering what solution to use, and the one that seems the most promising is this one in picture. So basically moving those two properties into a subnode, add-on ID, which kind of looks like let's hide that under the carpet to some extent, but I'm looking at you, Christophe, Connor. If you have better ideas, I'm all ears. That seems something that would work. Implementation should be just a few additional lines of code to locate the node and pass that to whatever NVMe function takes a node pointer. That's our current plan. Any better ones would be very welcome, of course.
Isn't there some resemblance with the board ID stuff from Qualcomm?
Kind of, but the problem here is that you should not add the properties to the other device node, right? So, and the Qualcomm solves totally different problem. But I don't think that you will be solving the same problem. So, just looks the same, coincidence.
No, in this case, you add a reference to a place where you can read the ID. In the Qualcomm case, you would put the ID inside the DT, which means that you need a different overlay. If you would do the same here, you would need a different overlay for each thing. But then you need to know which one to load, which is the chicken and egg problem.
Yeah, right. There are other ideas about NVMe, but they are way less promising, so I'm not even mentioning them. About the implementation itself, I'm going to quickly introduce how the connector driver works, which is conceptually very, very simple. So it it detects there's something connected to a GPIO. It loads the first overlay and populates the device in that, so up to the memory with the ID of the board. And based on that, it loads the second overlay with everything else, and then it populates that, and that's all. Everything is present in Linux, is used, and when the connector is removed, which happens without notice, so that's not super nice, but immediately the driver unloads the two overlays in reverse order. That's working pretty well in the practice, except for the issues with some specific aspects that I'm going to mention. So the one that is at the moment the most blurry one, and hints and discussion would be extremely welcome on this, is how to handle GPIOs and interrupts. So differently from I2C, platform devices, DSI, and whatever, this is not easily solvable by just adding nodes, which is the main goal, because you have a GPIO controller handling interrupts also on the baseboard, and you have users on the add-on board, which normally have a P handle into the pointing to the GPIO controller. We cannot have P handles reference across the overlay boundaries to avoid, well, to decouple the baseboard from the add-on, and also to avoid the memory leak issues. So we need some solution. This is some, yes, Gert? Mike?
Can't you use the Nexus node for that? GPIO Nexus, interrupt Nexus?
What?
Nexus node. It's in the device tree specification. It's basically some translation layer for GPIOs or interrupts.
Okay.
Across a node boundary.
If you can give me a specific pointer to that, I will look at that, Charlie.
I'm pretty sure that the most recent version of the Beagle Play connector thing is using it. So you can take a look at that for what they're doing.
Okay, so you mean the microbus patch series?
Yeah, like there's a version. God, it's not listed here. It's listed as, it went back to version 0, but check out the unversioned, most recent version of that from like this current week, and they've switched to that.
Okay, we'll check that out.
Mike. Search for Nexus in the specification.
Okay, yeah. So, well, just to mention our approach for discussion, it's actually something that we still have to test, so it's just theory for now. So something we attempted and it doesn't work is to have the GPIO controller in the base, in the main board, a normal GPIO controller, and then in the overlay we just repeat the same node without adding nothing. So it's just looking like an empty node, but we add a label. That's trying to add a label inside the overlay. It doesn't work. This is discarded explicitly by the overlay loading code in the kernel. And even if we disable that line, it breaks somewhere else. So no, that was just a wild attempt. The other wild attempt, we did this one, which is again, so it's somewhat similar. There is a GPIO controller on the, well, a GPIO something on the baseboard with it's based on the GPIO aggregator. So it points to actual GPIOs from other controllers on the baseboard. It aggregates them. But then in the add-on, we add a subnode, and that subnode has GPIO controller, GPIO interrupts, and the cells. So it kind of looks like a GPIO controller provider. And it has a label which is used inside the overlay itself. So that's an idea to attempt. So this is just maybe looking like, again, moving things into a subnode. I don't know. So this is just one of the, I don't know how the other Nexus proposal works, so I have no idea.
Well, how they solve on Nexus the p-handle issue, in fact.
Yeah, how does it?
How do you reference some?
For example, for interrupts, I think it uses interrupt map and interrupt map mask. So the interrupt map is then an array of p-handles and specifiers, which takes care of the translation. And when the child node refers to that one, and you look up a GPIO, then the core OF code will notice that there's an interrupt map, and then it will follow the map to the upstream interrupt controller. And it's similar for GPIOs. Yeah, PCI uses something similar.
I don't think that interrupt maps will solve the issue because when we wrote a line from the interrupt map array, you know, it's an array of several items, and in one items, you have to refer with a p-handle the interrupt controller in the interrupt maps to do the translation.
So he's saying basically the Nexus node, I'm assuming if I understand you correctly and kind of guesstimating here, it'll be part of the baseboard, which says this is how we map the interrupt coming from my child nodes into the main interrupt controller. And then if you add the overlay underneath it, is that what you're saying?
Handle do you put to the overlay? The problem is here that the overlay can be applied to different boards, right? So what sort of handle would you put to the overlay? I mean, like, what sort of label would you reference via handle? You don't know. I mean,
the one I really
you don't have an access because the overlay is to this board or that board. Right?
I really want to have a p-handle telling my GPIO on my connector, GPIO A on my connector, whatever the connector I am plugged in fact.
The map needs to be on the base overlay, but the p-handle needs to reference something inside the overlay.
Yeah, I think to phrase it differently for all the buses, be it I2C or GPIO or DSI or whatever, the devices on the add-on should only know the bus they're using on the connector, maybe A, B, C, and then the thing that describes the main board then maps that to the buses of the SoC. So maybe bus A on the connector is I2C1, but on a completely different baseboard, that's I2C bus A would be I2C5 or whatnot. So we need to strictly decouple the two, so the overlay cannot know what's on the baseboard, but only the signals on the connector. I think it's really that. Yeah.
Really quick, in Zephyr, we addressed that problem with what we call Zephyr chosen nodes, which is like just an arbitrary device tree alias to a p-handle that a board would mandatorily define if they want to use such an interface. Oh. Let's see if I can, let's have an intermediate maybe, or let's.
No, that's more question to you. So, but you cannot alias the particular GPIO. You can only alias the node, I think. But, so you cannot say that this is GPIO A, because that's a GPIO number 13 on the GPIO controller tree.
You can. The GPIO aggregator, which allows you to partition the entire GPIO controller. So basically, you can make one GPIO a new controller. So this is how you alias it. Yeah, it's different binding.
Yes, so
probably this has been already discussed with the Beagle and with the Nexus node. Like, can we really have the connector node in the root of the device tree, well, under the root of the device tree, because that seems like a board device, and then but basically describe that it has links to, and then you need a special driver for that, for the connector that really just passes through all the buses and everything. Probably I'm missing a point in that.
I think the main point is we need to do a two-step decoupling, like take the I2C. So there is this I2C debut, which is just the name of an I2C line that crosses the connector. This node on the base tree associates these two wires on the connector are coming from I2C2CH1 from the baseboard. it does the association on the side of the fixed board. And then on the overlay, we do the association from the connector to the devices. We cannot associate directly the controller to the device because that would make the overlay not portable.
That's clear. I mean, you had the issue with the interrupts and with the GPIOs, if I got it correctly. So why can't you describe them in exactly the same way? Tell that your adapter or your connector is a GPIO controller, and it provides, I don't know how many, 10 GPIOs, and then you map inside the bindings, you tell that, yeah.
You mean the connector is a GPIO controller?
Yeah.
Yeah, that makes sense, except the problem, we cannot have a p-handle, like a device on the add-on has a p-handle interrupt or GPIO blah blah equals and a p-handle pointing to the connector, because the connector is a node in the base tree.
Yeah,
you cannot reference anything in the base tree. We need a node that is inside the overlay.
Why can't you reference the base tree? I mean, if it is labeled, you can.
No, because that would make it.
Property leaks in symbols nodes.
Yeah, there is the issue with property leaks when you're adding properties, but also that you are not decoupling the add-on from the baseboard.
Yeah, you can have multiple connectors. You can have multiple of the same connectors and multiple of the subboards, but you can play with the symbols, which is what one of the other patch series is doing.
Yes, but that reintroduces the memory leak problem with the properties. So we are doomed.
Add more memory.
Okay, so my takeaway is that our solution kind of sucks, but there is no better proposal, obviously perfect. So, well, we'll experiment with that. Yep, that's all, I think. We had
many other.
Yeah, many other aspects, but so basically platform devices are already quite well handled by the driver. I2C devices, due to the flooding, Wolfram could not come, so we can discuss that, I guess. DRM was discussed 2 days ago in another session, and we have a bunch of issues related to DevLink, which we discussed with Saravana. We had a very long lunch break with Saravana yesterday. There is some path forward. I'd be glad to take more questions, but not sure time is.
Could you talk a bit more about this dead props problem? Because if you have symbols, you can just add a new label. You can have more than one label for the same node. So the only problem that remains is this dead props problem, which, so can you talk a bit about
that problem exists since forever with overlays. So if an overlay adds a property into a node, but the node is in the live tree, so it's not inside the overlay, properties don't have ref counting. And so what happens is any driver can take your property, can take the string, take a pointer to that, and nobody knows when it will stop using that. So if you release the property when you remove the overlay, you could have dangling pointers, use after free. To avoid use after free, the OF core, the device tree core, doesn't release them. It puts them into a dead properties list, and it never deletes them, basically. So that's considered a memory leak.
In fact, it will be released when the node containing the properties is going to be released. Yeah. But it's not on the base tree, and it's never been released.
And there is anyway another aspect which is more, let's say, philosophical design issue. So that was something I discussed with Rob Herring. And so the idea is if you add a piece of hardware, typically you should add a node, which is true for what we do with I2C and with platform devices, but there are gray areas like these interrupts and GPIOs, which are not easily manageable. So that's why that's the main topic. Yeah, thank you. Thank you, everybody.
of more discussions on the device tree, it would be great if you could take them outside so we can have the next one.
Hello, everybody. My name is Skylar Patton. Co-authored this presentation with Andrew Davis, a colleague of mine at TI. And what we're talking about... Oh, sure. All right. I'll try to lean in. How's that?
Yeah,
I don't really talk that loud, so I'll just lean in. So anyway, we did this presentation to kind of talk about how we can connect MCUs to MPUs. This has been, well, real quick, I work in our Sitar MPU group. Andrew also works in our embedded processing. He's part of our open source technology team. But let me get on to the presentation here. So connecting MCUs and MPUs has been done for a long time. What I wanted to highlight here, this is kind of like we were talking earlier about the CAN presentation with the J1339. Those are for like defined implementations. This is what I'm going to talk about is more about user-defined things, about just connecting one or two things up that perhaps didn't make it into the X application that's in the MPU. And again, these are things that have been around for a long time. And one thing we're seeing a lot is a lot of MCUs being attached to MPUs, and they're doing very simple things, not sophisticated things, like the CAN thing was just presented earlier. I'm pretty sure everybody knows what an MPU is, but it's the Linux thing on the left, and the thing on the right is the MCU. And those are typically very, very cheap. Everybody likes to pay an MCU price for an MPU, but that obviously we can't do that. So some common applications that I've seen is one of the things I've been working with a little bit lately is EV charging. And so for just a couple peripherals we don't have, like on one of our MPUs, is a PWM and an ADC. They're kind of being run specifically on the MCU, and they're being run at a very, very high rate. We can't be bothered on the MPU. We've also seen like touchscreen controllers. Wireless protocols is another example of thing I think was talked about earlier that connect typically over UART. But one of the things I'm going to talk about here in a second is when you don't have a UART and we have to maybe perhaps switch to a SPI interface. And sometimes that causes some grief for developers. Low latency apps, we see a lot. Peripheral mismatch is the other thing I'm talking about. So like on one of our MPUs, we didn't have an ADC, and the only way to get that was to add in an MCU. And to do that, we had to use a SPI interface. And so typically, when you're connecting up two MCUs, an MCU to an MPU, you have just a couple of different interfaces that you can use. For example, most people use UARTs. You could also have a SPI interface. We're suggesting maybe I2C, but also one of the things I was thinking about would be, could we use a CAN interface? So a lot of times you're seeing CAN being used for other things than a normal, like say, CAN application. Seeing a lot of just basic data transfer instead of being more of a command and control or status update type thing. We're seeing like things like firmware uploads happening over CAN bus. And those are happening at very high rates. The thing that the CAN maintainer talked about, frame drop, we see that a lot because people are going really fast on the CAN bus. But when you connect up the interfaces, is that you have to, like we already have these defined interfaces. Typically, it's in the dev directory. We have I2C and SPI and the UART. And CAN's in the network side of things, but we're wondering if maybe we could make it more into a UART. And this is kind of where we're seeing sometimes an issue, is that on the MPU side, you can run out of interfaces pretty quick due to muxing. And so normally when you have a UART to UART type thing, that's fairly straightforward. But what if, say for example, you're out of UARTs on the MPU, and you have to maybe switch over to, a lot of people switch over to SPI next, but could you switch over to CAN and still be able to interconnect the two devices? And I can't say this, I mean, usually on the MCU side, we have these SDKs are getting pretty sophisticated now in terms of being able to switch interfaces pretty quickly. But I'm speaking from the MPU side, where you want to be able to have maybe one application that you can just use, and it's connected over UART, but now you're underneath, you're going to connect with SPI or I2C or even CAN. And that's kind of what we're trying to say is, can we perhaps kind of have something that always looks like a UART even though you've got a different underlying bus. And so like with UARTs, everybody's pretty much familiar with, you can just, you can cat in interface. That's a real quick way of testing it. Again, these are standard applications that come in most file systems, and you don't have to worry about having to compile anything. And also the last point is that with a UART type application, it's a little bit more straightforward to some application developers. If they think they have to use SPI, then it kind of introduces some support issues in terms of people not understanding SPI applications or SPI-based applications. And the other thing is that a lot of times when people see, like if they're using a SPI bus, they expect a dedicated driver. And if you don't have to have a dedicated driver, it allows people to develop a lot faster. And that was, I would say, one of the things we'd see a lot. That prohibits a lot of people from just connecting MCU up because they think they have to have a dedicated SPI driver. And UART would be something that's, again, this is simplest. It's very straightforward, lots of examples on the web. And most people understand that. And as an example, this is like a hello world type user application that's based on a UART. And that you simply just going to open and then read it and then do whatever you need to do and then maybe go back to sleep. And again, everything from this application would look like it's just another peripheral that's attached to the device over UART. So in this right here, these are some common, I guess, MCU solutions that you see a lot, how they're connected. This is not all of them, but for example, the one on the left is the standard UART, where you have maybe say an ADC is connected to the UART on the MCU, and then that's connected to the UART on the SoC. And then you have the standard UART driver, so going down to the bottom where you see the dev TTY as 0, that's how you write it for your application. All three of these are versions of being able to just access a simple UART. The one in the middle is the one that we kind of like to highlight. The one in the middle is one we want to highlight here, is that a lot of times when you're having more sophisticated, you have an RP message type stack. And there's also apparently, according to Andrew was showing us, that you can do an RP message TTY, which gets you back into a UART context rather than having to do a lot of the RP message type applications. So again, that kind of simplifies your UART, your application from a UART perspective. And then the one on the right is just another example of like a USB coming in over a UART. But one of the things we're seeing is sometimes perhaps people don't like a USB because the device may not have USB. And if you're going from a USB to a UART, you're back into having to have like a conversion chip on the board, which is something we talk about here. So a couple things about it, maybe expanding like SPI for UARTs is that with the SPI, you can have multiple chip selects. So you could actually connect multiple MCUs on the SPI, but it'll still make it look like a UART. Again, this is highlighting simple data. This is not going to be sophisticated MCU applications like you have a MCU that's running for like a motor control type app. This is for more simple sensor-like data. Again, we're not highlighting. We'd like to see if we could just have a UART interface. So this is the key slide I think we wanted to show you. Is that the red box is kind of showing how can we take whether we have a SPI dev driver or some other thing and have it come through this one box and run it through a pseudo TTY type application. And then that way you can still have your Linux application, still looks like it's talking to a UART even though you've got this underlying different connection mechanism. So the thing on the right also is a similar thing in that I'd like to maybe see if we could add CAN in there. I know CAN's part of the network stack, but could we add that in there? Yeah.
Yeah, I was just going to say it's basically like tunneling into more complex protocol.
So one more thing I wanted to highlight about this one I kind of skipped over is that right now you can already kind of do
just to be sure that I understand. This means that you also on the MCU side need to have a protocol to to serialize the SPI transfers, right?
Yes.
Okay.
So the reason.
So the idea is to define a standard protocol like our P-message is already a standard protocol, but a standard protocol for SPI and for CAN and for I2C to serialize them.
So the I kind of talked about, well, but to your point, like a lot of these MCU SDKs now come with complete driver libraries, and they already kind of have example code on how they can access the interface. Is that what you're talking about in terms of like a?
So in general, when you write code for an MCU with a SPI interface, you're going to define commands on the SPI, and with the command has a well, you expect one SPI frame to be one command. Like you don't need special links and so on, and you maybe piggyback or already response on the same SPI transfer. Which does not map at all over to UART, right? So basically you will need to have a specific protocol on the MCU side as well that both sides agree on to be able to have UART on top. And on top of that, probably a application-specific protocol still to do the actual functionality.
No, yeah, I agree with what you're saying on that. And that was kind of what I'm not showing here. One thing we did is that you'd have. This is going to be a higher level, like user-defined protocol. So you're just using this as an underlying bus. You'd still have to, like what you're saying is your user would have to define the commands you're trying to push across that.
Yes, I know. Just like with UART, you send a stream of bytes and you receive a stream of bytes. With I2C and SPI, you can just do the same. But I2C, you have to be careful because there's a slave address. Excuse me? Yeah, sure, but yeah. It's just a stream of bytes that you're sending and receiving, like with the UART. And you have to, at a higher level, you have to define some protocol, which is probably commands separated by a new line or something like that.
Yes, right.
But when you do I2C transfer, you need to chunk into transaction. Is it 8 bits, 16 bits, 32 bits? I mean, SPI is the same, right? So you still need to define a way. And so just taking a step back, isn't that taking the problem from the wrong angle? What is your MCU providing as feature? Because normally the kernel exposes to user space some device that provides some actual feature. Is it an ADC? Is it a timer? Is it a watchdog? What is the feature that it provides? Because here you're only abstracting the communication channel, but normally the management of the feature is on the kernel side, and we expose to user space applications some more high-level feature like a network interface, an audio interface, something like that. So I think the real question is, what is your MCU doing, and shouldn't that handling be done on the kernel side? We have some use cases where we have a remote MCU that has ADCs, and we have an IIO driver in the kernel that communicates with the remote MCU, and it's exposed as a regular IIO device from the standpoint of the use space application. So we're not abstracting the communication channel, but just making a normal driver fitting in the right subsystem. So I think this is handling the problem from a slightly wrong angle from my perspective.
I think both problems exist. Depending on the use case, you have one or the other.
Yes. Just have a simple shell that you're talking to. You read ADC, write ADC, write DAC, things like that.
I don't see how you can do it generically. So if you are using SPI, the other device needs to poll you somehow. So you actually send something to it to receive something on the other side, and you need a lens. How many cycles do you give it so it returns to you? So you need a protocol. You just can say, yeah, we just map UART. It's more complex than that. And I agree, we also have this use case in a lot of projects. These industrial people love their microcontrollers. And we normally want it always in the kernel because they have watchdogs, they have like CAN. We have like a customer who does CAN over SPI because, yeah, I have an STM32. Of course it has to CAN, I want to use that. And yeah, our P message over SPI and over UART in the kernel, that would be great.
Okay. I mean, I'll talk to you more about that one. All right, so 3 minutes. Well, the only thing I wanted to highlight next is whether we do this at the user level or at the kernel level. kind of what you're talking about. Is it at some point, latency is going to come into the picture in terms of how fast we can respond. And so therefore, that would have to be taken into account. And then also there's a flow control aspect. Is it how much data is too fast? How do we control it? Yeah, this was more thinking about this would be from a very simple data perspective. Ideally, wouldn't be too time sensitive, but again, these things are also, these are the points you bring are all good ones. And maybe UART abstraction might be something that might be a very simple interface that you could use across different interfaces. But we can always discuss whether this would be.
Any more questions?
Serial sounds simple, but in practice it's not always that simple. So are you aware of any small command line tools that you can use to talk to a microcontroller in such a way? For example, I have something similar in my board form. I have a microcontroller with USB serial, and I talk to it with a simple shell commands like GPIO1 on or things like that. And what I need and what I still haven't finished is basically some simple command line tool where I could, that would just pass the parameters as one line to the serial and then read back until it gets the prompt back.
We don't have that, but because the application we were doing was basically it's just dumping data from the ADC to the SPI. Maybe you have one.
Yeah, have you heard of Zephyr? Because we have a really great shell. So there are shell applications for virtually everything, like GPIO, and it does have a prompt, which is really good.
So we're in the wrong place today.
No, it's not the Zephyr side, the microcontroller side. It's on the Linux side.
Thanks, everyone. See you next year.
Oh, yeah. So we selected one for the overlay stuff, and then the other one we